past the last planets, 2 human-made ghosts are still flying, Voyager 1 and 2, silent, unstoppable, and alone. Long after their power dies, their momentum keeps writing a path through the dark between stars. When 1,000,000 years pass and Earth is unrecognizable, where will they be? And what will their trajectory reveal about our moving, changing galaxy? 1,000,000 years is long enough for continents to forget their names and for the night sky to rearrange itself. Yet 2 artifacts of Earth keep their course, indifferent to every ending we can imagine. To follow them, we have to abandon the comforting idea of a fixed map. Space is not a backdrop, but a moving argument. The sun drifts through the Milky Way at a speed that makes our fastest probes feel like sparks trailing a torch, and the boundary they crossed is not a wall, but a living surface, wrinkled by solar storms, threaded by magnetic fields, and pressed by interstellar wind. Soon the last engineered signals will thin into silence, not with drama, but with arithmetic. Power fades, heaters go cold, antennas lose their perfect aim, and what remains is pure motion. In that quiet, the Voyagers become something rarer than machines. Test particles, marking the solar system's passage through a galaxy that refuses to stand still. But a 1,000,000-year prediction is not a single line drawn into darkness. It is a calculation with a moving origin, a choice of reference frame, and a sky that will not keep its constellations. Tiny uncertainties in direction widen into corridors across tens of light years. Then gravity, dust, and passing stars add their own slow, patient edits. The result is not a guess and not a prophecy, but a disciplined range of futures. We will build that range from first principles, how the planets gave the Voyagers their final push, why their paths diverged, and what it truly means to leave the heliosphere. We will watch the solar system itself sweep onward, so that where becomes a relationship between motions, not a pin on a chart. And we will ask what could disturb an interstellar coast, impacts too small to notice at once, forces too weak to matter in a year, and encounters too rare to plan for. Because the stakes are not whether these probes survive as functioning spacecraft. The stakes are whether we can locate them in deep time at all, when the galaxy has carried their birthplace far away, and when our own records may be as fragile as their fading transmitters. Somewhere ahead lies an answer that is both numerical and unsettling, a coordinate that doubles as a kind of memory. So we begin with a paradox, 2 silent travelers that cannot turn back, and a home system that is also traveling. If we want to know where they will be, we must first learn what where means when everything moves. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across the chapters, we'll trace their escape, cross the sun's invisible frontier, and then shift to the Milky Way's larger stage. At the end, we'll assemble the 1,000,000-year position as a probability corridor, clear enough to grasp, vast enough to humble. Voyager 1 drifts in interstellar darkness, a small machine in a large quiet, with no sunrise and no nearby world to reflect light. Its antenna no longer points with certainty, and its heaters ration warmth as power fades. In the cold beyond the heliosphere, even metal seems to hold its breath, while the spacecraft's slow spin turns starlight into a faint, periodic glint. For decades, it spoke in a thinning radio whisper, weaker each year with distance, spreading outward like ripples that flatten across a cosmic ocean. The Deep Space Network hears that whisper with giant dishes and careful timing, pulling meaning from noise by integrating signals for long minutes. That whisper is not a mystery of will or luck. It is physics and time, written in inverse square laws, and the relentless bookkeeping of thermodynamics. Voyager's electricity comes from radioisotope thermoelectric generators, steadily declining as plutonium decays and heat becomes harder to harvest. Inside each RTG, plutonium-238 releases energy as alpha particles, warming a ceramic core that never truly stops glowing in infrared. Thermocouples then convert a fraction of that heat into electricity, exploiting a temperature difference that shrinks as the system ages. As watts fall, instruments shut down one by one to preserve the last essential functions. And each shutdown is a small surrender to entropy. Engineers do not simply flip a switch and walk away, because every watt has a purpose, and every heater prevents a line from freezing. They choose which sensors can be sacrificed, which transmitters can be throttled, and which subsystems must survive a little longer. Commands take many hours to arrive, and confirmation takes many more. So even routine decisions unfold with a slow, delayed gravity. The final signal will not be dramatic, just a last carrier lost in noise, like a candle extinguished at the far end of a long tunnel. Mission Control will listen, confirm, and then accept the inevitable silence, because the telemetry will no longer close its link budget. The story most people tell ends there. The camera fades to black, the music resolves, and the legend becomes a memorial. But space does not care about mission status, budgets, or human attention. When the power fails, the probe does not stop, because nothing out there reaches in to grab it. It keeps moving, because inertia is destiny, and the universe is generous with time. This is the misconception at the heart of Voyager's legend. We treat end of mission as end of journey, as if silence means stillness. In the vacuum between stars, those are different events separated by immense time, and the separation is the point. Voyager 1 and Voyager 2 become relics, but also something else. Something more scientific than sentimental. They become long-lived test particles, tracing the solar system's motion through the galaxy and sampling a region where direct measurements are rare. Their trajectories keep recording history without sending it back, because motion itself is a durable archive. 1,000,000 years is the scale that makes this clear, because it is long enough for continents to shift and for coastlines to redraw themselves. It is long enough for civilizations to rise and vanish, yet short in galactic terms, where stars complete orbits over hundreds of millions of years. It is a span where the sun moves, stars drift, and gravity slowly edits every path, like a patient hand changing a manuscript. 1,000,000 years is about 10,000 times recorded human history, and it dwarfs the lifetimes of empires that once seemed permanent. It is several times longer than Homo sapiens has existed as a distinct species, and far longer than any technology has endured without caretakers. It is time deep enough to erase languages, borders, and names, leaving only geology and starlight as reliable witnesses. It is also a distance scale, and distance is the currency of space. Light travels 1 light year in a year, so 1,000,000 years is 1,000,000 light years of travel for a photon, crossing a significant fraction of the Milky Way's disk. Voyager will not go that far, but the comparison resets intuition, because it reminds us how slowly machines move compared to light. The documentary's promise is simple and hard. We will calculate where Voyager 1 and Voyager 2 will be in 1 million years, using the best physics we have and the best catalogs we can trust. We will trace the routes they take through and beyond the solar system, and we will be honest about what can be known and what must remain a range. To do that, we start with facts that anchor the myth, because legends float unless they are pinned to dates and numbers. Voyager 2 launched first on August 20th, 1977, beginning the grand tour that depended on a rare planetary alignment. Voyager 1 launched on September 5th, 1977, taking a faster path that prioritized Saturn's moon Titan and a quick exit. The window was narrow, and the opportunity would not return for many lifetimes. Their names mislead, because Voyager 1 reached key milestones first, and history remembers arrivals more than schedules. It flew past Jupiter and Saturn, then aimed upward out of the planetary plane, climbing above the ecliptic like a diver leaving a bright, shallow reef. Voyager 2 visited Jupiter and Saturn too, then continued to Uranus and Neptune, turning a 2-planet mission into a 4-planet odyssey. In archival footage, the spacecraft are clean and bright, their gold insulation catching sunlight near Earth. In the outer solar system, that sunlight thins to a hard, distant glare, and the probes become points against velvet. Today, they are the most distant human-made objects, farther than any spacecraft that came after, and their distance is measured not in miles, but in light hours. Voyager 1 is the farthest, already in interstellar space beyond the heliosphere's boundary, where the solar wind no longer dominates the surrounding plasma. Instruments recorded the change as a shift in particle populations and magnetic conditions, marking a crossing that is more physical than symbolic. Voyager 2 followed, crossing later on a different heading, and its data confirmed that the boundary is lumpy and dynamic rather than smooth. They are not traveling in the same direction, and that difference will matter more as time stretches. Voyager 1 is headed roughly toward the constellation Ophiuchus, on a path tilted above the ecliptic, climbing into a region of sky that looks calm only because it is far away. Voyager 2 is headed roughly toward Sagittarius, on a path angled below the plane, diving toward a denser-looking star field near the galactic center's direction. These directions are not just trivia, because the sky is a map of future encounters, and every line through it intersects moving targets. A heading determines which stars the probe will pass near, and which gravitational nudges it might receive, even if those nudges arrive as gentle, cumulative tugs. Over 1 million years, small deflections matter, because a tiny change in angle becomes a vast change in position. The central question is not whether Voyager will die, because we already know the batteries of heat will cool and the transmitters will fall silent. The central question is where it will be when our era is a footnote, and when the launch date is just another number in a long chronology. 2 silent machines will still be moving, and their motion will still mean something, even if no one is listening. To predict that future, we need a framework that matches the time scale, and we need to resist the temptation to think only in solar system terms. We must treat the solar system as a moving object inside the Milky Way, embedded in a rotating disk of stars and gas. We must treat the galaxy as a gravitational field that never turns off, because gravity does not retire when a mission ends. The first ingredient is the probe's current velocity vectors, which are more than speeds on a fact sheet. We need speed and direction relative to the Sun, not relative to Earth, because Earth's own orbit adds a seasonal wobble. We need the best navigation solutions, built from decades of Doppler tracking and ranging, because errors today become large distances tomorrow. Even a millimeter per second of uncertainty, stretched across 1,000,000 years, becomes a corridor of possibilities. Voyager 1 is leaving the Sun at about 17 kilometers per second, and Voyager 2 at about 15 kilometers per second, coasting on momentum gained from planetary flybys. Those numbers are fast by human standards, but modest compared to stellar motions, where tens of kilometers per second are ordinary. Over 1,000,000 years, they still add up, turning steady speed into a long, quiet migration. At 17 kilometers per second, Voyager 1 covers roughly half, a light year in 1,000,000 years, a distance that sounds small until you picture the emptiness between stars. That is far beyond the planets, far beyond the Kuiper Belt's brighter members, but still within the Sun's local neighborhood. It will not reach another star unless a close pass comes to it, and close passes are governed by chance and galactic traffic. The second ingredient is the solar system's own motion through the Milky Way, because the Sun is not a fixed lamp in space. The Sun orbits the galactic center at roughly 220 kilometers per second, carrying planets, comets, and spacecraft along for the ride. Voyager rides inside that larger flow, like a boat crossing a moving river, and its outward drift is a small diagonal across a much larger current. This matters because where is always relative to a frame, and frames are choices with consequences. In the Sun's frame, Voyager moves outward on a nearly straight line, gradually slowing as solar gravity steals a little kinetic energy. In the galaxy's frame, Voyager is a small offset from the Sun's long arc around the center, and the two paths remain neighbors for a surprisingly long time. The third ingredient is gravity, working patiently over long durations. And gravity is never only one thing. The Sun's pull weakens with distance, but it never becomes zero. So the probe remains loosely bound in a practical sense for a long while. The giant planets can still shape trajectories, even after the last close flyby, through tiny, long-range effects that accumulate like interest. Beyond the planetary region, the solar system's mass distribution and the faint tug of distant bodies add subtle curvature to what looks like a straight line. Beyond the planets, passing stars become important, and the sky's calm is an illusion created by human lifetimes. A star that comes within a few tenths of a light year can bend a trajectory measurably, changing the probe's future by shifting its aim. Most passes are distant, but over 1,000,000 years, the odds of a meaningful encounter rise, because the Sun itself moves through a crowded stellar neighborhood. There is also the galactic tide, the collective pull of the Milky Way's disk and halo, acting like a slow, persistent gradient. It is subtle, but it can slowly change orbits in the outer solar system, lifting and lowering distant objects over long cycles. It shapes the Oort cloud, and it can shape anything traveling through that region, including a small spacecraft that seems, at first glance, too insignificant to matter. The fourth ingredient is uncertainty, which compounds with time and refuses to be ignored. Navigation errors, unknown outgassing, unmodeled forces, and imperfect star catalogs all widen the cone of possible futures, even when the physics is correct. 1,000,000 years turns small uncertainties into vast corridors, And those corridors are part of the truth, not a failure of calculation. So we are not promising a single pinpoint, because the universe does not offer that kind of courtesy at this horizon. We are promising a best estimate, plus a range, plus the reasons that range exists, stated clearly and without romance. We are promising to show which forces dominate and when the forecast becomes probabilistic, because probability is how science speaks when determinism becomes impractical. This is where the story becomes more than nostalgia and more than a museum label attached to a famous mission. Voyager is not only a symbol, it is a measurable object obeying mechanics, and mechanics does not care what we hoped for. If we can follow its path, we can also understand the solar system's place in a changing galaxy, and we can ask what it means to leave a trace that outlasts our ability to watch it. The golden record was designed as a message in a bottle meant for unknown hands, and it carries diagrams meant to survive translation across minds. Yet the bottle itself is also a message, written in motion, and motion is a language any gravity well can read. Its trajectory says where humanity was, and where the sun was at the moment of launch, embedded in the Milky Way's rotating frame. 1,000,000 years from now, the record may still exist, even if no one plays it, because vacuum is an excellent preservative. The spacecraft may tumble, its surfaces sandblasted by dust grains at interstellar speeds, each impact a microscopic crater made by a grain smaller than smoke. The radio will be dead, but the orbit will remain, and the path will still point back to an origin that may no longer remember it. There is a quiet drama in that contrast, and it is the kind of drama space specializes in. The voice fades quickly on cosmic scales, but the journey continues for ages, and the continuation is almost indifferent. The machine becomes a moving fossil, carrying a timestamp through the dark, and inviting a question we rarely ask. What else in our world will still be moving when we are not? To understand that journey, we have to begin close to home. We have to know how Voyager is moving right now, through the solar system's outer frontier, where the sun's influence thins and the interstellar medium presses back. We have to replace myth with mechanics, step by step, so the future we describe is earned rather than imagined. Next, we map the present trajectory precisely, then extend it outward into deep time, letting small angles become large separations. We start with the sun, the planets, and the heliosphere, because the first push determines the 1,000,000-year path, and because every long story begins with an initial condition. Voyager did not leave on sheer engine power. It left on borrowed momentum, taken in tiny fractions from giant planets that never noticed the theft. In the inner solar system, rockets provide the first shove and the first direction, and they do it with a violence you can see. After that, fuel becomes precious, and gravity becomes the real propulsion system, silent and relentless. A gravitational assist is not magic, and it is not free energy. It is a controlled exchange of momentum between a fast-moving planet and a lighter spacecraft, arranged so the spacecraft departs with a different velocity vector. The key word is vector, speed, and direction together, because you can change a mission's destiny without changing its speed very much. In practice, the assist can do both, but the geometry decides which you get. Picture cosmic billiards, but with curved paths and invisible cushions. The spacecraft falls toward a planet, swings behind it, and departs with a new speed and heading, as if the planet had flicked it with a moving hand. Visually, the approach is a tightening arc, the planet swelling from a bright point into a disk with bands and storms. The radio signal stays steady, and the trajectory, already computed, threads through space like a needle. In the planet's own frame, the spacecraft arrives and leaves at nearly the same speed. The planet's gravity acts like a reversible engine there, bending the path without permanently speeding it up. In the Sun's frame, the planet's orbital motion tips the balance and changes the spacecraft's energy. The spacecraft can depart with a higher heliocentric speed because the planet itself is already moving around the Sun. The trick is timing and geometry, not brute force. Pass behind the planet's motion, and you can steal a tiny piece of its orbital momentum, leaving on a trajectory that is rotated and often accelerated. Pass in front of the planet's motion, and you can do the opposite. You can give momentum back, breaking yourself into a tighter solar orbit, which is useful for some missions, but not for the Voyagers. That stolen piece is minuscule for Jupiter or Saturn, lost in their enormous mass and angular momentum. For a spacecraft, it is life-changing, turning a bound orbit into an escape. The bookkeeping is strict, even if it feels like a cheat. Total momentum is conserved, and energy is conserved too, but the energy is redistributed between bodies in a way that favors the lightweight traveler. Jupiter was the first great dealer of momentum for both missions. Its gravity well is deep, and its orbital speed is high enough to reshape trajectories dramatically, especially for a probe arriving from the inner solar system. On screen, Jupiter is not merely a planet. It is a moving mountain of mass, wrapped in clouds, dragging space-time into a steep slope that a spacecraft can fall down. The encounter is a fall inward and a climb outward, like dropping into a valley and exiting on a different ridge. The ridge you reach depends on your aim by kilometers, and those kilometers are chosen years earlier. That aim is set by a parameter engineers call the closest approach distance, and by the angle of the incoming asymptote. Change either slightly, and the outgoing asymptote swings wide, like a compass needle. Voyager 1 and Voyager 2 both used Jupiter to bend their paths and raise their heliocentric energy. Their outbound lines began to separate, even before Saturn entered the story, because each flyby was tuned to different downstream needs. The tuning was not casual. Navigation teams used Doppler shifts and ranging, then ran trajectory solutions that included Jupiter's moons and its non-uniform gravity field, because Jupiter is not a perfect sphere. Saturn was the second and decisive table in this cosmic game. It offered another chance to trade angle for speed, and to choose a future that could not be undone. Saturn's gravity is weaker than Jupiter's, yet its role was strategic. It could tilt a trajectory out of the planetary plane or keep it near the ecliptic for further encounters. By the late 1970s, mission planners knew the alignment was rare. The outer planets were arranged so one assist could set up the next, like a chain of falling dominoes across decades. That alignment had been calculated long before launch, and it shaped the entire program's urgency. There was a window in which Jupiter, Saturn, Uranus, and Neptune could be visited in sequence without impossible fuel demands. That alignment did not guarantee success, and it did not guarantee the same outcome for both probes. It offered options, and options forced a choice about what mattered most: speed, targets, or the chance to go farther. Voyager 1 took the faster route to Saturn, arriving first despite launching second. The mission prioritized Titan, Saturn's largest moon, because Titan was a scientific prize and a mystery wrapped in haze. At the time, Titan's atmosphere was suspected but not measured in detail, and its surface was completely hidden. A thick atmosphere meant chemistry, weather, and possibly prebiotic processes, an alien laboratory at the edge of sunlight. Titan's thick atmosphere demanded a close flyby to measure and infer its composition. That close pass also demanded a specific geometry, and geometry demanded sacrifice. Close meant close in navigational terms, where a small error could shift the altitude by tens of kilometers. It also meant threading between Saturn's gravity, Titan's pull, and the need to keep antennas pointed home. To reach Titan on the desired line, Voyager 1 had to accept a trajectory that kicked it out of the planetary plane. After Saturn, its path tilted upward relative to the ecliptic, like a stone skipping off a tilted surface. That tilt is not just a visual flourish. It is a change in inclination, a reorientation of the orbit's plane, and it is expensive to do with engines, but cheap to do with a well-placed gravity assist. Voyager 2 faced a different mandate. It was tasked with continuing the grand tour, aiming for Uranus and Neptune after Saturn, which required staying closer to the ecliptic. So its Saturn flyby was designed as a bridge rather than a finale. The trajectory had to leave Saturn on a line that would intersect Uranus years later, with almost no opportunity for correction. That single divergence in goals created two different roads into interstellar space. One road climbed above the solar system's flat disk. The other dipped below it, remaining nearer the crowded lanes of planetary gravity. In the language of celestial mechanics, the ecliptic is the reference plane of Earth's orbit. Most planets stay near it, so leaving it changes what you can encounter later and what can still tug on you. Voyager 1's Titan choice traded future planetary visits for a clean exit. Voyager 2's continuation traded a slower escape for a longer tour of the outer giants and for a more complicated gravitational environment. These are not just historical footnotes. They are the initial conditions that will dominate the million-year forecast, because direction matters as much as speed, and direction is where the missions truly diverged. A small change in outbound angle today becomes a huge lateral separation over deep time. Over 1 million years, a fraction of a degree becomes light years of difference, and the probes stop being siblings in any practical sense. The solar system threw them outward, but it did so with precision. The final push was not a single event, but a sequence of gravitational negotiations, each one narrowing the next set of possibilities. After the last major flyby, the spacecraft entered a simpler phase. Engines were mostly silent, and the trajectory became a long coast shaped by the sun's fading pull, with only occasional attitude changes and course trims. To say they are escaping, we need a definition that does not depend on drama. Escape velocity is the speed needed to never return on a closed orbit, given a particular distance from the sun. Escape velocity is not a universal number. It drops with distance, because the sun's gravitational potential weakens as you climb outward, and the hill you must clear becomes less steep. If you are below escape speed at a given distance, the sun can keep you bound in an ellipse. If you are above it, your path becomes open and unbound, and the spacecraft becomes a visitor rather than a resident. For the Voyagers, the relevant fact is their orbital energy relative to the Sun. Their energy is positive, which means their trajectories are hyperbolic, not elliptical. Hyperbolic does not mean straight, and it does not mean gravity stops. It means the spacecraft will not loop back into a repeating orbit around the Sun, even if the Sun continues to tug at it forever. The Sun still slows them as they climb outward, converting some kinetic energy into gravitational potential. Yet even after that slowing, they retain enough excess speed to keep going, like a ball still rolling after cresting a hill. This is where reference frames quietly change the story. A speed quoted relative to Earth is not the same as a speed relative to the Sun, and mixing them can create the illusion of sudden accelerations. Earth carries its own orbital velocity, and it adds a seasonal vector to any measurement. Navigation teams remove that motion to get a heliocentric velocity that is physically meaningful for solar escape. Even heliocentric is not the only choice. The solar system has a barycenter, a center of mass that shifts as Jupiter and Saturn move, and it is a cleaner dynamical reference when you care about long-term motion. In a barycentric frame, the Sun itself wobbles slightly. In a heliocentric frame, we pretend the Sun is fixed, which is useful but not perfectly exact, especially over long spans. For narrative purposes, we use heliocentric speeds as a stable anchor. We also admit that exact values vary with time, modeling choices, and the frame you adopt, because precision depends on definitions. Today, Voyager 1 is moving at roughly 17 kilometers per second relative to the Sun. Voyager 2 is moving at roughly 15 kilometers per second relative to the Sun, and that difference compounds into very different futures. Those numbers are order of magnitude truths, not a single eternal constant. They drift as the probes climb farther, and as gravity continues to trade speed for distance, slowly shaving kinetic energy into altitude. 17 kilometers per second sounds abstract, so we translate it into the solar system's own currency. At that speed, Voyager 1 covers about 3.6 astronomical units per year, crossing the scale of planetary orbits with steady inevitability. An astronomical unit is the average Earth-to-Sun distance, and it is the yardstick of planetary space. At 3.6 AU per year, the probe crosses the scale of planets quickly, even though it feels motionless in the black. Stretch that rate across 1 million years, and the arithmetic becomes unsettling. Ignoring perturbations, Voyager 1 would travel about 3.6 million AU in that time, a number so large it stops behaving like distance. Convert that into a more familiar stellar measure, and it becomes about 57 light years. That is not a promise, and it is not a plotted destination. It is a first crude answer, useful, blunt, and incomplete. The crude answer is useful because it sets the scale of the question. Voyager is not crossing the galaxy, but it is leaving the Sun's neighborhood in a way planets never do, entering the sparse geography between stars. Yet the crude answer is also misleading, because it treats space as empty and fixed. 1 million years is long enough for the background to move under the foreground, and for the foreground to be gently deflected. The Sun is not parked in space while Voyager departs. The Sun and its planets sweep around the Milky Way at hundreds of kilometers per second, orbiting the galactic center along with billions of other stars. That motion does not change the probe's speed relative to the Sun, but it changes where the entire system is relative to nearby stars. The launch point itself is moving, carrying the whole story along. So the question becomes two questions at once. Where is Voyager relative to the Sun in 1,000,000 years? Where is Voyager relative to the stars that also drift, each with its own proper motion? Before we can follow either, we need a way to talk about direction. In deep space, direction is a vector, but humans remember directions as patches of sky, like landmarks painted on a dome. Astronomers use celestial coordinates to label those patches, projecting Earth's coordinate ideas onto the sphere of distant stars. The labels are convenient, not physical signposts, and they evolve as Earth's axis slowly precesses. When we say Voyager 1 is headed toward Ophiuchus, we mean its line of travel points toward that constellation from our current viewpoint. Ophiuchus is not a target it will reach, because the stars are far and moving. When we say Voyager 2 is headed toward Sagittarius, we mean its outbound direction aims toward that crowded region of sky. Sagittarius is a backdrop, not a destination, and it is crowded precisely because we look toward the Milky Way's center. Constellations are patterns, and patterns are accidents of perspective. Over 1,000,000 years, the stars that form those patterns will shift, and the labels will lose their meaning, like a map drawn on drifting ice. Still, the sky directions are a useful shorthand for the present headings. Voyager 1 climbs above the ecliptic toward northern ecliptic latitudes. Voyager 2 dives below it, into southern ecliptic latitudes. Those different ecliptic latitudes matter because the solar system is not spherically uniform. The planets, most small bodies, and much of the dust lie near the ecliptic plane, where gravity is busier and collisions are more likely. A path that leaves the plane quickly reduces the chance of later interactions with planets. A path that stays nearer the plane remains in the neighborhood of massive movers longer, and it stays closer to the Kuiper Belt's broad, flattened distribution. Even without another close flyby, gravity continues to act. The sun's pull bends the trajectory slightly, and the combined field of planets adds tiny, long-range perturbations, like distant hands tugging on a taut thread. These perturbations are small each year, but they never stop. Over long spans, small accelerations integrate into meaningful changes in position and timing, and the uncertainty grows even if the physics is deterministic. The million-year separation problem is mostly geometry. If two objects leave with slightly different directions, their distance apart grows roughly linearly with time, even if their speeds are similar. A 1-degree difference would create a lateral separation of about 1 light-year after 57 light-years of travel. Even 1/10 of a degree becomes 1/10 of a light-year, which is still vast compared to any planetary scale. The Voyagers differ by more than a trivial fraction of a degree in their outbound headings. Their separation will become enormous compared to the scale of the solar system, and even compared to the size of the Oort cloud. This is the tension hidden inside clean numbers. We can quote speeds to the kilometer per second, yet a tiny angular uncertainty can dominate the final position after deep time, turning a point into a widening cone. Navigation teams measure velocity with Doppler tracking, reading frequency shifts in the radio signal. They also use ranging and long-term fits to refine the full-state vector, including position, velocity, and the subtle biases of instruments. Those measurements are excellent by human standards, and they were extraordinary achievements for the 1970s. Yet perfection is not required for the present mission, because the goal is to understand the near-term environment, not to hit a star. A million-year extrapolation demands a different kind of humility. It asks you to respect how error scales, and how even tiny forces, ignored in short arcs, can bend a path over geological time. Even a millimeter per second of uncertainty becomes tens of thousands of kilometers per year. Over 1,000,000 years, that becomes a corridor wide enough to swallow planets, and wide enough to make "where" a probabilistic statement. Angle errors are even more unforgiving. A micro-radian error becomes millions of kilometers of cross-track distance after enough time, and the cone of possibilities widens until it dwarfs the tidy line on a chart. So, we carry two truths at once. The trajectory is well known now, and it is still uncertain when stretched to 1,000,000 years, because the future is an accumulation of small unknowns. The uncertainty is not only measurement error, it is also unmodeled forces that are too small to matter today, but too persistent to ignore forever, especially when you integrate them over immense spans. Outgassing is one example, when tiny leaks or material releases create a faint thrust. Thermal recoil is another, when heat radiates unevenly and produces a minute push, photons carrying momentum away in a preferred direction. Interstellar dust impacts are mostly negligible, but over long durations they can add noise. The spacecraft's attitude changes can also change how small forces accumulate, because the cross-sectional area and thermal patterns shift. Then there is the environment itself, which is not empty. The interstellar medium has plasma, magnetic fields, and neutral atoms, and it pushes back in subtle ways, like a thin wind you cannot feel. At Voyager speeds, the drag is extremely weak, but it is not mathematically zero. Over 1,000,000 years, even weak effects can become part of the accounting, especially if the medium's density changes along the route. More important than drag is gravity from outside the solar system. Passing stars, molecular clouds, and the galactic tide all add slow, persistent perturbations, and they act on both the spacecraft and the sun. A stellar pass does not need to be close to matter. Over enough time, even a distant encounter can bend a trajectory by arcseconds, and arcseconds become huge distances later when multiplied by light years. The sun itself experiences those encounters, and its own path is nudged. That means Voyager's future relative to the sun and relative to the galaxy can diverge in subtle ways, depending on which reference you care about. This is the first layer of mystery that the numbers cannot erase. Space is not static, and the map is not printed on paper. The map is moving while we read it, quietly, continuously. Even the sun's neighborhood changes. Stars drift with their own velocities, and the sun passes through different local clouds and different gravitational textures, like a ship crossing invisible currents. So the naive calculation of 57 light-years is a baseline, not a prophecy. It assumes constant speed, no deflections, and a background that politely holds still, which the universe does not do. We keep the baseline anyway, because it frames the scale of the journey. Voyager 1 is not merely leaving the planets. It is entering the domain between stars, where distances are measured in years of light. To make that domain real, we return to the last push that made it possible. Jupiter and Saturn did not just speed the probes up. They aimed them into different parts of space, and they did it with the cold elegance of orbital mechanics. Voyager 1's Saturn encounter, shaped by Titan, sent it onto a steeper path out of the ecliptic. That choice reduced later planetary influence and simplified the escape, at the cost of ending the grand tour early. Voyager 2's Saturn encounter preserved the geometry needed for Uranus and Neptune. That choice kept it nearer the ecliptic longer, and it left on a different outbound heading, carrying the mission's ambition forward. Both outcomes are triumphs of planning because the assists required precise arrival times. A miss by minutes at Jupiter would have meant a miss by hours at Saturn, and a miss at Saturn could have erased entire chapters of discovery. The assists also required faith in models, because the spacecraft were navigating through complex gravitational fields. The planets are not perfect spheres, and their moons add complications, and even small uncertainties in mass distributions matter. Yet the core principle stayed simple. Fall in, swing around, and leave with a new vector, paid for by a planet's orbital momentum, as if the planet had lent a spacecraft a tiny fraction of its own motion. The planet does not slow in any measurable way because the exchange is spread across an enormous mass. The spacecraft changes completely because it is small and easily redirected, and because its entire future is encoded in that new line. This is why the solar system can throw things out without explosions. A gravity well can act like a slingshot, and the slingshot can be aimed with mathematics, equations turned into a flyby altitude. Now we can state the present-day situation cleanly. Both Voyagers are on hyperbolic trajectories relative to the Sun, and neither will return on a closed orbit, even if their radios fall silent. Voyager 1 is departing faster, around 17 kilometers per second heliocentric, on a path aimed roughly toward Ophiuchus. Voyager 2 is departing slower, around 15 kilometers per second, aimed roughly toward Sagittarius. Those headings are not fixed in an absolute sense because the coordinate grid is human-made. They are a snapshot of a vector in a universe where everything else also moves, including the stars we use as reference pins. The last push is over, but the consequences are just beginning. The smallest differences in the 1970s are now written into the sky as diverging lines, and those lines will keep opening like the arms of a slow compass. Over 1 million years, those lines become separations so large that the solar system looks like a point behind them. The probes become independent travelers, sharing only an origin and a fading signal that once tied them to Earth. But we cannot follow them with straight-line arithmetic alone. The medium they traverse has structure, boundaries, and changing pressure from the Sun and from the galaxy. And those boundaries define what leaving really means. Speed gives us a crude distance. The real story begins when that speed carries them through the Sun's frontier and into the interstellar flow. Next, we cross the boundary that defines the solar system's reach in plasma and magnetic fields. We follow Voyager through the heliosphere into interstellar space and beyond. Speed gives us a crude distance. The real story begins at the Sun's frontier, where a wind becomes a wall. Out beyond the bright planets, beyond the last strong glare of reflected sunlight, the solar system does not end in a line. It fades into gradients, pressure against pressure, field against field, until a familiar dominance quietly gives way. The heliosphere is the Sun's bubble in space, inflated by the solar wind and carved into the local interstellar medium. It is not a solid shell, and it is not even a single surface. It is a dynamic pressure boundary, shaped by solar cycles, magnetic fields, and the sun's motion through nearby gas. In simple terms, the solar wind is a continuous outflow of plasma from the sun's corona. It is mostly protons and electrons, with traces of heavier ions, and it carries embedded magnetic field lines outward. Near Earth, it can be hundreds of kilometers per second, but it expands and thins as it spreads through space. Inside this bubble, the solar wind dominates. Charged particles stream outward, carrying the sun's magnetic field like a spiraling thread. That spiral, an effect of the sun's rotation, turns the field into a vast wound structure that can guide particles and shape shocks. The wind thins with distance, but it still sets the rules for plasma, radiation, and particle transport. Even when the density drops to almost nothing by terrestrial standards, the collective behavior of charged particles still matters. In plasma, fields and flows can act like invisible architecture. Far from the planets, that outward flow meets resistance. The interstellar medium pushes back with its own pressure, its own magnetic field, and its own population of particles. The result is a layered frontier that is measured, not seen, an edge traced by instruments rather than eyes. The interstellar medium is not a vacuum in the everyday sense. It is a thin mixture of ionized gas, neutral atoms, and dust, threaded by magnetic fields that are weak in absolute units. Yet those fields can dominate charged particle motion across enormous distances because the particles are so sparse. As the sun moves through its local neighborhood, it plows a wake through this material. The heliosphere responds like a living boundary, swelling and shrinking as the solar wind strengthens or weakens. It also distorts because the interstellar magnetic field presses more on some directions than others. The first major boundary is the termination shock. Here, the solar wind drops from supersonic to subsonic speeds as it begins to pile up. Supersonic in this context means faster than the speed of sound in the plasma, a speed set by temperature and magnetic conditions. When the flow crosses that threshold, it cannot smoothly communicate changes upstream. The solar wind must shed energy and reorganize, and a shock forms, like a traffic jam that becomes a sudden wall. The flow heats, turbulence rises, and the neat outward stream turns into a slower, compressed plasma. Visually, the termination shock is not a crisp ring. Imagine a dim, rippling boundary, wrinkled by solar storms and shaped by the sun's tilted magnetic axis. In some regions, it may be pushed inward. In others, it may be farther out, breathing with the cycle. Beyond the termination shock lies the heliosheath. It is a thick, disturbed region where solar wind plasma is slowed and diverted, trying to find a way around the external pressure. The plasma here is hotter and more chaotic, and it carries the memory of earlier solar conditions. Magnetic fields twist, particle populations mix, and the boundary breathes with solar activity. The heliosheath is also a factory for energetic particles, because shocks and turbulence can accelerate ions to high energies. Those particles become part of the radiation environment that spacecraft must endure. At the far edge is the heliopause. This is the contact surface where the solar wind's dominance ends and interstellar plasma becomes the surrounding medium. It is not a clean sphere, and it is not fixed in place from year to year. It is a warped, shifting shoreline, changing with time and direction. In some models, it resembles a comet-like shape, with a blunt nose into the interstellar flow and an extended tail. In others, it appears more rounded, but always asymmetric. This is why the heliosphere works as a narrative threshold. On one side, Voyager is a solar probe in the Sun's extended atmosphere, still inside a region ruled by solar wind pressure. On the other side, Voyager becomes an interstellar artifact, moving through a medium that belongs to the galaxy. That change sounds like a single step, but it is more like crossing a foggy beach at night. The sand underfoot changes grain by grain, and the air changes salt by salt, until the old landscape is behind you. The instruments become the only sense organs that can testify. Voyager 1 approached this frontier on a path above the ecliptic, and it reached the heliopause first. In 2012, its instruments recorded a sharp change in particle environment consistent with crossing into interstellar space. The moment was debated, then strengthened by later analysis and additional measurements. The debate was not about drama, but about definitions and data. The heliopause is not a painted line, and the spacecraft did not carry a sign that could be photographed. Scientists had to infer a boundary crossing from multiple sensors that each measured a different part of the environment. The key evidence was not a camera shot. It was a set of sudden, coordinated changes in what the spacecraft could count and feel. Energetic particles associated with the heliosphere dropped, and the particle populations that had been trapped or guided by the heliosphere thinned. Galactic cosmic rays increased as if a shield had thinned. These are high-energy particles, often protons or atomic nuclei, accelerated by distant astrophysical events and guided by galactic magnetic fields. The heliosphere acts as a partial modulator, reducing their intensity inside the bubble. Magnetic field behavior also shifted. The field strength rose and became more stable, consistent with a different plasma regime. That stability matters because turbulence inside the heliosheath can cause rapid fluctuations, while the interstellar field can appear smoother over similar times. The direction of the field did not rotate as dramatically as some expected, which revealed the boundaries' complexity and the limits of simple cartoons. In early expectations, a sharp change in direction seemed likely at a contact surface. Instead, the field lines appeared more draped and connected than a clean break suggested. Plasma density became a decisive clue. Voyager 1's plasma instrument was no longer functioning, but the spacecraft could still infer density from plasma wave oscillations. When electrons in a plasma are disturbed, they can ring at a frequency tied directly to density. Those oscillations indicated a higher density typical of the local interstellar medium, not the tenuous solar wind. The numbers were small in everyday terms, but the contrast was telling. It was like stepping from a thin mist into a slightly thicker haze, detectable only with careful instruments. Voyager 2 provided a second crossing and a cleaner instrument suite. In 2018, it crossed the heliopause on a different trajectory below the ecliptic. Its working plasma instrument directly measured the solar wind fading and the interstellar plasma taking over. That direct measurement mattered because it reduced ambiguity. Instead of inferring density from waves alone, Voyager 2 could sample the plasma flow and temperature more straightforwardly. The crossing became a second anchor point, another stake in an invisible shoreline. The two crossings did not match perfectly. That mismatch was the point, and it was scientifically useful rather than inconvenient. It showed the heliosphere is asymmetric, shaped by the interstellar magnetic field and by the sun's changing output over the solar cycle. In other words, the heliopause is not at one universal distance. It shifts with direction, and it shifts with time, because pressure balance changes. A stronger solar wind can push the boundary outward, while a quieter sun can let it drift inward. Scientifically, these crossings mattered because they were the first direct sampling of the boundary region. Models of the heliosphere had to be tested against real data rather than inference. The Voyagers turned a theoretical border into a measured place, with numbers that could be argued over and refined. They also connected decades of heliophysics to a tangible milestone. The idea of a solar wind bubble emerged in the space age, when spacecraft first measured the wind's speed and variability. Over time, that concept matured into global models that could predict where shocks and boundaries might lie. The heliosphere also matters because it modulates radiation. It deflects and slows some cosmic rays, and it shapes how charged particles enter the solar system. Crossing the heliopause is not only a change of scenery, it is a change in shielding and a change in what kinds of particles dominate the environment. Inside the heliosphere, solar energetic particles from flares and coronal mass ejections can dominate at times. Outside, the steady background of galactic cosmic rays becomes more prominent, and the spectrum changes. The difference is subtle in a single day, but profound over long exposure. Yet one misconception persists because the word leaving is slippery. Leaving the heliosphere is not leaving the sun's gravity, and it is not leaving the solar system in every sense. Plasma boundaries and gravitational boundaries are different maps drawn on the same space. The heliosphere is defined by pressure and magnetic influence. Gravity is defined by mass and distance, and it never switches off. Voyager can cross the heliopause and still be linked to the sun by a weak, continuous pull that fades but does not vanish. This matters for the million-year question because it separates two kinds of reach. The sun's electromagnetic reach ends at a boundary that can be crossed in decades, at least by fast spacecraft. The sun's gravitational reach extends far beyond, shaping trajectories for millions of years. A useful concept is the sun's Hill sphere, the region where the sun's gravity dominates over the galactic tidal field for bound orbits. It is roughly a light year in scale, depending on definitions and local galactic conditions. It frames the outer limit of stable solar ownership, not the end of influence. The Hill sphere is not a fence, and it is not a guarantee. It is a region where long-term stability is possible, provided other disturbances remain modest. Beyond it, the galaxy's tidal pull and passing stars can more easily unbind objects over long times. Even beyond the Hill sphere, the sun still exerts force. Gravity falls with distance, but it remains part of the sum of forces acting on Voyager. Over long times, small accelerations can still bend paths, especially when combined with passing stars and the galactic tide. So Voyager's identity changes at the heliopause, but its mechanics do not become free of the sun. It becomes less a solar mission and more a drifting test particle in the galaxy. The sun remains a reference point, even when it is no longer the dominant plasma source. Outside the heliopause, Voyager enters the local interstellar medium. This medium is thin by Earth standards, but it is not empty. It contains ions, electrons, neutral atoms, dust grains, magnetic fields, and a steady rain of high-energy cosmic rays. Here, the visuals shift from bright planetary vistas to near blackness with sparse stars. The spacecraft becomes a small, cold geometry in a vast field, its antenna dish catching faint starlight. The emptiness is real, yet it is structured, filled with fields and particles too small to see. The density is low, often described as fractions of a particle per cubic centimeter, varying with local clouds and conditions. The Sun is currently inside a region sometimes called the local interstellar cloud, a patch of slightly denser material within a larger cavity. That local geography changes on scales of tens of light years. The magnetic field is weak in absolute terms, measured in microgauss, yet strong enough to guide charged particles over large distances. A microgauss is tiny compared to a refrigerator magnet, but in space, the particles are so free that even a weak field can steer them. The environment is quiet, but it is not gentle. For an unpowered spacecraft, the interstellar medium becomes the long-term weather. There is no active station keeping, no course correction, and no protective magnetosphere. There is only inertia, weak gravity, and continual microscopic impacts. Dust grains strike at tens of kilometers per second relative speed, depending on the grain's motion and the spacecraft's heading. At those speeds, even a grain smaller than a speck of smoke carries kinetic energy enough to chip metal or pit a coating. Each impact is tiny, but over 1 million years the statistics add up. Surfaces slowly pit, edges erode, and coatings are altered by repeated hits. The damage is not dramatic like a collision in a movie, but it is relentless like sandblasting. Over long spans, the cumulative effect can change reflectivity, texture, and even the readability of fine engravings. Micrometeoroids and larger grains are rarer, but they carry more energy. A single larger impact could puncture insulation or damage the golden record cover, depending on geometry and luck. The probability is hard to pin down because the dust distribution is uncertain, especially on million-year horizons. The uncertainty is part of the story. Interstellar dust is not evenly spread, and the solar system moves through regions with different grain populations. Voyager's path could remain in relatively sparse material, or it could cross a denser filament, where impacts become more frequent. Over 1 million years, chance becomes a major variable. Radiation is the other slow sculptor. Cosmic rays and energetic particles can darken polymers and change surface chemistry. High-energy ions can displace atoms in crystalline lattices, creating defects that accumulate like invisible bruises. Metals can develop altered layers, and some surfaces can become more brittle. Paints and adhesives can embrittle, even in vacuum, under long exposure to high-energy particles. In plain language, radiation can make materials less flexible and more prone to cracking when stressed. Thermal cycling continues, even far from the Sun, because the spacecraft rotates and different surfaces alternately face starlight and deep space. The temperature swings are smaller than near planets, but they are persistent. Over long spans, repeated expansion and contraction can stress joints, foils, and layered materials. The spacecraft also carries its own radioactive heat sources, at least early on, which can create small thermal gradients. As power fades, internal temperatures drop, and the structure settles into a colder equilibrium. The transition itself is a mechanical event, changing stresses and possibly changing how the craft tumbles. Over 1 million years, the spacecraft will almost certainly become a slow tumbler. Attitude control will stop when power and propellant are gone, and the stabilizing influence of active pointing disappears. Without active control, the antenna becomes just another surface, and the craft's orientation becomes a random variable in its long-term evolution. That tumbling matters because it changes exposure. One side may face the interstellar flow for centuries, then turn away, then return. The pattern will be irregular, and small torques from uneven radiation pressure or impacts can gradually alter the spin state. The spacecraft becomes a drifting object with its own slow, silent choreography. The Golden Record is the most famous physical artifact on board, and its survival is a question of materials, science, and probability. The record is gold-plated copper with an aluminum cover designed to resist corrosion and micrometeoroid damage. It was engineered for endurance, but it was not tested on million-year timescales. In vacuum, chemical corrosion is minimal, which is one reason deep space preserves objects so well. There is no oxygen-rich air, no liquid water, and no microbial life to digest polymers. Yet preservation is not perfection, because impacts and radiation keep writing their signatures. Gold plating is stable, but it is thin. Pitting from dust impacts could eventually scar the surface, and high-energy radiation could alter fine details over long times. The cover offers protection, but it is not an absolute shield, and its effectiveness depends on impact angles and the craft's tumbling history. Even the cover's engraved diagrams, designed as a universal key, depend on surface integrity. If a future finder exists, would the markings remain legible after countless micro-impacts? Would the record's grooves retain enough fidelity to be decoded, or would the message become a textured relic without a voice? Longevity estimates are uncertain because the environment is uncertain. The interstellar medium varies, and the spacecraft's path may pass through denser clouds or quieter regions. 1,000,000 years is long enough for rare events to matter, and rare events are hard to model. Still, the baseline expectation is that much of Voyager's structure remains recognizable. Vacuum preserves shapes, and there is no weather in the terrestrial sense. The damage is slow and cumulative, written in micrometers rather than meters, and that scale difference is the key to its endurance. This is the quiet irony of interstellar space. The spacecraft dies as a communicator within decades, but it can persist as an object for geological time. The message may outlast the messenger's voice, drifting as a physical whisper long after the last signal fades. The boundary crossing also changes what Voyager can teach us, even after silence. Its trajectory becomes an inertial trace through a moving galaxy, a line that can be reconstructed long after the mission ends. Its surface becomes a long-term exposure experiment, recording the interstellar environment in scars and altered materials. But to answer the central question, we need to separate two calculations. Distance traveled is straightforward if we assume roughly constant speed relative to the Sun, and we accept that small perturbations average out. Position in the galaxy is not straightforward because the Sun itself is moving. This is where intuition fails, and where the documentary's tension can be built honestly. People imagine Voyager racing outward into the Milky Way, leaving the Sun behind like a parked car. The truth is that the Sun is also in motion, and it is moving fast enough to carry the entire solar system across interstellar neighborhoods. A common exaggeration appears in casual talk. In 1,000,000 years, the Sun will travel tens of thousands of light years around the galaxy. That sounds dramatic, and it feels right when we picture galactic scales, but it is wrong by orders of magnitude. The Sun's orbital speed around the Milky Way is about 220 kilometers per second. Multiply that by 1 million years and convert the distance, and the result is about 230 light years, not tens of thousands. The real number is still enormous on human scales, but it changes the story's proportions. That correction is more than a fact check. It reframes the scene. The Sun is not sprinting across the galaxy in a single lifetime of civilizations, but it is steadily translating through space. Over 1 million years, it carries its planets, its comets, and its departing probes into a new stellar neighborhood. Now compare that to Voyager. Voyager 1's speed relative to the Sun is about 17 kilometers per second, which corresponds to roughly 50 to 60 light years in 1 million years, in a simple, straight-line estimate. Voyager 2 is slower, closer to 40 to 50 light years over the same span, depending on the exact speed used. Those numbers are staggering, yet they are smaller than many people expect. They also hide a subtlety. Voyager's velocity is not aimed straight out of the galaxy, because there is no such simple direction. It is aimed along a specific departure path set by planetary gravity assists, and that path rides on the Sun's larger motion. The reveal is that Voyager's outward drift is small compared to the solar system's galactic translation. In 1 million years, the Sun carries everything hundreds of light years along its orbit. Voyager's separation from the Sun is tens of light years, a smaller offset riding on a much larger journey. That does not make Voyager's trip trivial. Tens of light years is still deep interstellar space, far beyond any bound solar cloud region we can easily visit. It does mean that where is Voyager must be answered in a moving frame, with the Sun as a traveling origin. So the heliopause crossing is not the end of the Sun's story. It is the end of the Sun's plasma dominance and the beginning of a different kind of navigation problem. Voyager becomes a marker that drifts away from a moving star, like a buoy set loose from a ship that never stopped sailing. To locate Voyager in 1 million years, we must track two motions at once. Voyager's hyperbolic escape relative to the Sun continues, weakly perturbed by gravity and passing masses. The Sun's own path continues around the Milky Way, carrying the launch point far from its original galactic address. That means the next step is not another boundary in the solar wind. The next step is a change of scale and reference frame, from heliophysics to galactic dynamics. We have to zoom out until the heliosphere is a small wake around a moving star. The invisible shore is crossed, but the larger ocean is not still. Voyager is now an interstellar artifact, and the galaxy is the stage that will decide its long-term neighborhood. To answer the central question, we leave the Sun's bubble behind and follow the solar system's orbit through the Milky Way. Voyager is not leaving a stationary sun. The launch point itself is in motion, carried by the Milky Way's gravity and embedded in a rotating disk of gas, dust, and stars. Even the airless pad and the tracking antennas were already moving, quietly, relentlessly, before the rockets ever ignited. To answer the central question, we need a larger map. We place the solar system inside the galaxy's architecture, then let both motions run forward together, because the spacecraft and the star that launched it share a common drift. The trick is to stop imagining a fixed backdrop and instead treat the Milky Way as the true reference stage. Start with orientation that does not require a textbook. The Milky Way has a center, a disk, and a halo, and gravity ties them into one rotating system that is old, massive, and still evolving. This is not a static sculpture, but a living structure shaped by mergers, star formation, and the slow settling of matter. In wide-field images, the disk looks like a luminous river. Dark lanes of dust cut through it, cold molecular clouds that hide newborn stars, and from our position, carve the sky into bright and dim patches. On screen, those lanes read like ink spilled across starlight, and they mark where hydrogen molecules and soot-like grains gather. The center is not just a point on a map. It is a crowded bulge of stars surrounding a supermassive black hole, and its gravity helps organize the galaxy's rotation even at our distant radius. The black hole is called Sagittarius AK, and its presence is inferred from stars whipping around an unseen focus in tight, fast orbits. Above and below the disk sits the halo. It is faint, extended, and dominated by dark matter, an unseen mass component inferred from how fast the galaxy rotates at large distances. The halo is the reason the outer disk does not slow down the way simple, visible matter would predict, and that mismatch is one of modern astronomy's most persistent clues. Astronomers use a galactic coordinate frame to describe directions. The galactic center is the anchor, and the disk plane is the reference surface, so up and down become meaningful in a cosmic sense. In visuals, the grid can fade in over the sky, lines of longitude and latitude that turn a star field into a navigable chart. That coordinate system is a practical tool, not a philosophical one. It lets us compare motions measured from Earth with motions measured from spacecraft, and it keeps the geometry stable when the sky itself is shifting. It also prevents a subtle mistake, confusing a direction on today's sky with a direction in the galaxy's long-term frame. Our sun sits far from that center, in the disk's suburbs. Its distance is about 8 kiloparsecs, roughly 26,000 light-years, which places us between major spiral structure and inter-arm space. That suburb is not empty, though. It is a region with star-forming clouds, old stellar populations, and the faint glow of diffuse gas. This location matters because the gravitational field is not uniform. The disk's mass density, the bulge's pull, and the halo's broad influence combine differently at different radii, shaping orbital speeds and long-term stability. Where you sit in the disk changes the balance of forces, and it changes which perturbations matter over millions of years. The sun does not orbit like a perfect circle on a clean track. It follows an almost circular path, with small epicycles and vertical bobbing through the disk, because the galaxy's potential is lumpy and time-dependent. Spiral patterns, giant molecular clouds, and even past satellite galaxies leave subtle fingerprints in that gravitational landscape. Epicycles are a useful mental picture. They are small oscillations around the average orbit, like a runner circling a track while also weaving slightly left and right. In more formal terms, they reflect how a star responds to small deviations from circular motion in a rotating potential. The vertical motion is equally real. The sun oscillates above and below the galactic plane on a timescale of tens of millions of years, passing through denser regions where gas and stars are more concentrated. Imagine a side-on view of the disk, and the sun's path becomes a gentle wave, never far, but never perfectly centered. For scale, one full lap takes about 230 million years. That timescale is a galactic year, and it dwarfs human history so completely that our entire species occupies only a thin sliver of one orbit. If Earth's history were a clock, the sun's last full circuit would span epochs that predate familiar continents. In that context, the Voyager missions are astonishingly young. They are not even a blink on the galactic clock, yet their trajectories already extend beyond the sun's protective bubble. Their departure from the heliosphere is dramatic in our time, but it is only the first step in a much larger, quieter translation. The sun's orbital speed is about 220 kilometers per second. That number is the hidden background speed of every planet, comet, and spacecraft, because they all inherit the sun's motion through the Milky Way. It is the baseline velocity that never appears in a launch broadcast, yet it dominates the solar system's absolute motion. It is also a number with a history. Astronomers inferred it from stellar motions and galactic rotation curves, and those curves became some of the strongest evidence that dark matter dominates the galaxy's mass budget. In the 20th century, the realization that rotation stays too fast at large radii forced a rewrite of what galaxies are made of. When you hear 220 kilometers per second, picture something tangible. Imagine a bright point racing across a dark stadium at hundreds of times the speed of a rifle bullet, yet taking hundreds of millions of years to complete one lap. The scale is so large that speed and patience coexist, and that contrast is the Milky Way's signature. Now compress time to 1 million years. At 220 kilometers per second, the sun travels about 230 light-years along its galactic orbit, sliding through a changing star field that will not resemble today's sky. In a visual time-lapse, the sun's path is a long, smooth arc, and the background stars smear into new arrangements. That distance is not a rumor or a metaphor. It is the simple product of speed and time, translated into the galaxy's own units, and it is large enough to cross multiple local stellar neighborhoods. Even if nothing else happened, that translation alone guarantees that our sky is temporary. A light year is not a unit of time. It is a unit of distance, about 9.46 trillion kilometers. So 230 light-years is a stretch of space that swallows our familiar constellations whole. It is also a distance where the sun's gravitational influence is no longer the dominant organizing force. Then compare that to Voyager's heliocentric escape. Voyager 1 is about 17 kilometers per second relative to the Sun, and Voyager 2 is about 15, after their planetary flybys set their final outbound directions. Those speeds are measured after the spacecraft have effectively escaped the deep part of the Sun's gravitational well. Those speeds are impressive by human standards. They are also modest compared to the sun's galactic motion, which is why the story changes when we stop thinking in strictly solar terms. The probes feel fast in mission control, yet they are slow compared to the star that carries them. Over 1 million years, that drift becomes tens of light years. Voyager 1 reaches roughly 50 to 60 light-years from the Sun in a straight-line estimate, assuming its speed stays close to its present asymptotic value. That estimate treats the craft as a coasting object, with only tiny accelerations accumulating in the background. Voyager 2 reaches somewhat less, closer to 40 to 50 light-years, depending on the exact long-term speed and small perturbations that accumulate from weak forces and changing geometry. The difference sounds small, yet over cosmic distances, it becomes a meaningful separation in the sun's wake. These numbers are not predictions of where the spacecraft will arrive. They are distances traveled relative to the sun, which itself is moving. And that distinction is the hinge of this chapter. Distance from the sun is one story, while position in the galaxy is another story running underneath. Here is the conceptual pivot that changes the story's proportions. Voyager's heliocentric velocity is modest compared to the sun's galactic velocity, so the spacecraft is more like a small offset than an independent traveler. In the galactic frame, Voyager is not sprinting away from a fixed origin. It is drifting from a moving one. In a million years, the sun's translation dominates the absolute position. Voyager's separation is a smaller offset riding on a much larger journey, like a spark drifting from a fast-moving fire. The spark's path matters, but the fire's motion determines where the spark ends up in the room. So, where is Voyager splits into two answers. There is the distance from the sun, and there is the position in the Milky Way, which depends on the sun's own orbit as much as the probe's escape. That split is why a single number can mislead, unless we also name the frame. The first answer is mostly ballistic drift. The second answer is the sun's galactic motion plus that drift, added as vectors, because motion in space is always relative to a chosen frame. Once you accept that, the geometry becomes less mysterious and more like careful bookkeeping. Vector addition sounds abstract until you name the pieces. One vector is the sun's velocity around the galactic center, and the other is Voyager's velocity relative to the sun, measured from tracking data and Doppler shifts. Those Doppler shifts are tiny changes in radio frequency, yet they reveal speed with exquisite precision. Add them head to tail, and you get Voyager's galactocentric velocity. Subtract them, and you recover the heliocentric story we started with, which is the one we usually tell in mission updates. The same physical motion can look radically different depending on which moving origin you choose. This is why the same spacecraft can look slow and fast at once. In the sun's frame, it crawls outward, while in the galaxy's frame, it rides a fast-moving star that never stops orbiting. The craft is a passenger on a much larger flow, one that began long before humans existed. A useful analogy is a bead sliding off a moving train. The bead's drift across the floor is real, but the train's motion sets the bead's absolute path across the landscape. The bead does not need an engine to travel far because the train supplies the main translation. For visuals, imagine the train at night. The windows streak past distant lights and the bead rolls toward the door. Its motion is small, yet it is carried far by the train's relentless speed. Outside, the landscape blurs into a single direction, and the bead's tiny detour becomes a trace within that blur. From far enough away, Voyager does not draw a straight ray from the sun's current position. It traces a corkscrew-like offset around the sun's own galactic track, because the reference point is moving while the spacecraft slowly departs. In a rotating frame, the offset can look like a spiral ribbon, trailing behind a moving point. The corkscrew is not because Voyager is orbiting the sun. It is because the reference point is moving, and the offset is carried forward through space, producing a helix-like geometry when plotted in a galactic frame. The helix is a bookkeeping artifact, yet it is also a beautiful way to see two motions layered together. In the simplest model, the Sun draws a long arc around the galactic center. Voyager draws a nearby arc, displaced by tens of light years from the Sun's arc, like two lines on the same moving ribbon. The separation is small compared to the arc length, but it is large compared to any map of the solar system. That displacement is the answer we can estimate cleanly. The absolute arc is the answer that requires the galactic stage, because it depends on where the Sun itself will be along its orbit. To speak honestly about where, we must always say which where we mean. We also need to say what we are ignoring and why. Over 1 million years, the galaxy is not a rigid carousel, and gravity is not a single central pull acting on a point mass. The Milky Way's potential evolves, and local structures add texture to what would otherwise be a smooth field. The Milky Way's mass is spread out. The disk, bulge, and dark matter halo create a gravitational field that changes with position, and that field is shaped by spiral structure and local inhomogeneities. Even a giant molecular cloud, massive, cold, and dark, can act as a small gravitational landmark in the Sun's vicinity. Even the concept of a spiral arm is subtle. Arms are not solid walls of stars. They are patterns of enhanced density that stars and gas move through, compressing clouds and triggering bursts of star formation. In a visual sequence, gas enters an arm, brightens with new stars, then exits, while the pattern persists like a wave. That field produces tides, not just attraction. A tide is differential gravity, meaning the pull is slightly different at slightly different locations. So two nearby objects can slowly separate or converge even without any thrust. The effect is gentle, but it is systematic, and it acts in preferred directions set by the galaxy's mass distribution. In the solar system, tides from the moon raise oceans. In the galaxy, tides from the disk and halo gently stretch and shear distant orbits, acting like an almost invisible hand on very large scales. If you could draw the forces as arrows, they would be nearly parallel until you zoom out enough to see their tiny divergence. This galactic tide matters most at the solar system's edge. It shapes the Oort cloud, where comets are bound so weakly that small nudges change their fates, turning long-period comets into visitors or ejecting them entirely. At those distances, the Sun's grip is more like a suggestion than a lock. Historically, the Oort cloud was proposed to explain why comets arrive from all directions. The idea implied a vast reservoir of icy bodies, and it also implied that the Sun's gravitational ownership fades into a contested borderland. It was a conceptual expansion of the solar system, one that replaced a neat boundary with a diffuse, vulnerable frontier. The same idea applies to a spacecraft, even though it is unbound from the Sun. Over long times, differential gravity can bend trajectories away from a naive straight line, especially when the separation becomes tens of light years. At that range, Voyager and the Sun are no longer sampling the same gravitational weather. The tide is weak, but it never stops. A tiny acceleration integrated over 1 million years can shift a position by enormous distances, because the effect accumulates steadily like interest on a small deposit. That accumulation is why long-term trajectories are never just straight extrapolations, even in empty-looking space. Still, we keep the hierarchy clear. The dominant term is inertial motion plus the Sun's translation, and the tide is a slow correction layered on top, important for precision but not for the basic scale. The tide changes the curvature and orientation, but it does not erase the central comparison of speeds. To make the tide intuitive, imagine the Sun and Voyager separated by tens of light years. They do not feel exactly the same galactic pull because they are not in exactly the same place within the Milky Way's gravitational field. The difference is small at any instant, yet it is persistent across the entire interval. That difference changes their relative motion very gradually. It can stretch the separation vector, rotate it, or slightly curve it, depending on direction in the galactic field and the spacecraft's orientation relative to the disk. In a diagram, the Sun to Voyager line slowly swivels, as if the galaxy were gently turning a pointer. The tide also provides a background that competes with solar gravity. It defines why the Sun's distant cloud is fragile and why long-term ownership of objects is conditional, especially near the boundary where the galaxy's pull rivals the Sun's. The border is not a wall, but a balance of influences that shifts with position. There is also an observational lesson hidden here. When astronomers model distant objects, they must decide which gravitational influences matter, and the answer changes with distance. What is negligible at Neptune becomes decisive at the Oort cloud. The same logic applies to a probe once it becomes, in effect, an interstellar object. In earlier chapters, we crossed the heliopause, a plasma boundary. Now we cross a different boundary, from solar mechanics to galactic mechanics, where the dominant forces and reference frames quietly change. The transition is not marked by a shock wave, but by a gradual swap in what terms dominate the equations. The galactic frame also forces a second correction. The stars around us are not fixed landmarks, and the constellations are not stable signposts, even though they feel permanent on a human lifetime. What looks like an eternal pattern is a snapshot of moving points caught in one brief arrangement. The local stellar neighborhood is a moving swarm. Typical relative stellar velocities are tens of kilometers per second, sometimes more, because each star has its own orbit and its own small deviations from the average flow. Some stars stream with groups, some wander alone, and some carry the memory of past gravitational encounters. Over 1 million years, tens of kilometers per second becomes tens of light years. That means the nearby star field rearranges dramatically on the same timescale as Voyager's drift, and familiar patterns dissolve. A line of 3 stars can become a triangle, and a bright anchor star can slide into an entirely new context. So when we say Voyager heads toward Ophiuchus or Sagittarius, we are naming a present-day line of sight. The stars that define that pattern will not hold still, and the spacecraft will not pass through a frozen mural. In the far future, the probe's direction will be described against a different tapestry. Think of the sky as a time lapse. Points of light slide relative to one another, some approaching, some receding, and the backdrop that guided ancient navigation becomes a dynamic map with shifting geometry. The Milky Way band itself changes subtly because dust, gas, and star-forming regions are not fixed in place. This matters for future encounters. A spacecraft's path is not plotted through a static gallery of stars, but through a crowd where every object has its own proper motion and its own gravitational influence. Even a distant pass can matter if the geometry aligns and the time is long. The Sun itself is part of that crowd. It has a peculiar motion relative to the local standard of rest, and it oscillates slightly above and below the galactic plane, adding a gentle vertical component to its otherwise circular orbit. That vertical component is small, but it adds a third dimension to what we often draw as a flat circle. Those details are small compared to 220 kilometers per second, but they matter when you ask which stars come near and when. In long-term projections, small differences in relative velocity can shift encounter timing by thousands of years. A near miss can become a closer pass, or a close pass can become a miss, with only a slight change in initial conditions. There is a deeper implication here. The Milky Way is not a quiet stage that holds still while actors move. The stage is moving too, and the choreography is written in gravity. If you could hear it, it would be a low, continuous rhythm, mass pulling on mass across vast time. Now the narrative shifts from certainty to probability. The basic drift is predictable, but the neighborhood is dynamic, and close encounters are stochastic, meaning they depend on rare events and sensitive initial conditions. The future becomes a set of plausible paths rather than a single guaranteed line. We can separate the future into two components. One is ballistic, meaning the spacecraft coasts with small, smooth forces, and the other is encounter-driven, meaning rare. Close passages can dominate the deflection. The first is steady and easy to estimate, while the second is intermittent and hard to forecast. A close stellar passage is not science fiction. Over millions of years, the Sun experiences many approaches within a few light years, and some are closer because the disk is crowded and stars share the same general orbital lane. The galaxy is spacious, yet the statistics of time make encounters inevitable. Most passes are distant enough to be gentle. A few can be close enough to noticeably perturb Oort cloud comets, and in extreme cases they can shift small bodies substantially, sending some inward and flinging others out. Those perturbations can seed future comet showers long after the passing star has moved on. This is one reason impact risk is a long story. The comets that occasionally visit the inner solar system can be nudged by distant stars long before they ever see the Sun again. The cause and effect are separated by time so long that they feel unrelated, unless you track the gravitational chain. For Voyager, a close pass could change the trajectory more than the galactic tide does. It could also change the Sun's path slightly, altering the relative geometry, although the Sun's enormous mass makes its deflections modest. In the visual language of vectors, an encounter is a kink, small in angle, large in consequence. The problem is that we cannot list those encounters with certainty a million years ahead. We do not know the future positions of all nearby stars with perfect precision, and the errors grow with time as uncertainties propagate. Even with excellent measurements today, the uncertainty balloons as we integrate forward. Even if we knew every star's present state perfectly, the system is still sensitive. Small differences compound, and the cone of possible futures widens because gravitational interactions are continuous and the galaxy is not perfectly smooth. The Milky Way's potential has substructure, and substructure is where long-term predictions lose sharpness. This is the core of uncertainty and chaos in long-term celestial prediction. Deterministic laws can still produce outcomes that are practically unpredictable beyond a horizon, especially when rare close encounters act like sudden course changes. The math stays lawful, but the forecast becomes a probability distribution. We should be precise about what that means. It does not mean anything can happen, and it does not mean the calculation is pointless, because physics still constrains what is plausible. The spacecraft cannot teleport, and it cannot reverse direction without a force. The uncertainty is about which small forces will matter most. It means the forecast must be expressed as a corridor, not a single line. The corridor is narrow for ballistic drift, and it widens when encounters are allowed, because each possible encounter adds branching alternatives. In a visualization, the future path becomes a translucent tube that thickens with time. Measurement uncertainty contributes to that corridor. Small errors in Voyager's present velocity become large position uncertainties when multiplied by 1,000,000 years, and the effect is amplified when the direction is not known perfectly. Even a fraction of a degree, barely noticeable on a diagram, can become light years of lateral offset. Angle uncertainty is especially unforgiving. A tiny error in direction becomes a huge cross-track offset after tens of light years of travel, because the sideways component grows linearly with distance. The farther you go, the more a small pointing error becomes a wide miss. Model uncertainty also contributes. Tiny forces like thermal recoil, dust impacts, and changing attitude can add small biases that integrate over time, even after the spacecraft are long past active control. These are not dramatic thrusts, but persistent whispers that slightly reshape the long arc. Thermal recoil is a subtle example. Heat radiated unevenly from the spacecraft can act like a faint thruster, and although the acceleration is minuscule, it persists for as long as the heat sources remain. The effect is a reminder that even passive objects can generate forces simply by how they emit energy. Dust impacts are another quiet actor. Interstellar grains are sparse, yet over immense distances they can impart tiny impulses, and they can also slowly erode surfaces, changing how the spacecraft radiates heat. Each impact is negligible, but the cumulative statistics over millions of years are not automatically zero. But the biggest unknown is the future gravitational weather. The galaxy provides a steady tide, and the moving stars provide intermittent kicks, and the combination defines how predictable the far future can be. The question becomes, how smooth is the road, and how many unexpected bumps lie ahead? So we build a best estimate framework that is honest about limits. First, assume no unusually close stellar encounters, meaning no strong kicks within the 1,000,000-year window, and treat the galactic tide as a gentle curvature correction. This is not a claim that encounters will not happen, only a baseline against which surprises can be measured. Under that assumption, Voyager's distance from the Sun grows roughly linearly with its heliocentric speed. The Sun to Voyager vector is a simple extrapolation with small curvature corrections, because the spacecraft is essentially coasting. The probe's path is then a clean, readable trace, an arrow that lengthens steadily with time. Then place that offset onto the Sun's galactic path. Voyager's galactic position is the Sun's position after 1,000,000 years, plus the spacecraft's offset vector, which is the cleanest way to connect the two frames. In a composite animation, the Sun's arc appears first, then Voyager's offset peels away like a thin filament. That statement sounds simple because it is. It is also the backbone of every more detailed simulation, which adds tides, epicycles, and encounters as refinements rather than replacements. The complexity does not overthrow the main idea. It decorates it with corrections that become important only when you demand precision. In practice, astronomers implement this with numerical integration. They step the equations of motion forward through time, using a model of the Milky Way's gravitational potential and a catalog of nearby stars with measured proper motions. Each step is small, but the accumulation is vast, and the computer becomes a time machine for orbital dynamics. Those catalogs have improved dramatically in the modern era. Space astrometry missions have measured stellar positions and motions with unprecedented precision, tightening the near-term corridor even as the far future remains probabilistic. Better data narrows the tube at first, even though it still widens as time stretches outward. We can now restate the scale in one breath. In 1,000,000 years, the Sun moves about 230 light-years along its orbit, while Voyager 1 drifts about 50 to 60 light-years away from the Sun, and Voyager 2 drifts somewhat less. The numbers are simple, but their meaning is profound, because they reveal which motion dominates the story. The absolute location is dominated by the Sun's journey. Voyager's separation is the local detail, the offset that turns one moving point into two. And that offset is what makes the probes useful as markers. They are not merely far away. They are separated from us in a way that can be plotted against the galaxy itself. This is why the Voyagers are tracers of a galactic orbit. They are not just leaving, they are marking the solar system's motion through the Milky Way with physical artifacts, small machines that have escaped the Sun's immediate grasp. In a sense, they are the first human-made objects to write our star's motion into interstellar space. There is something haunting in that idea. The spacecraft carry records of Earth, but they also carry a measurement of our motion, because their paths encode the Sun's speed like a signature written across interstellar space. The signature is not carved in stone, but it is etched in trajectory. An orbit's handwriting. Even after their transmitters fall silent, their trajectories remain. They become inertial witnesses, showing that the solar system was never parked, only passing through, and that home is a moving target. If someone found them far ahead in time, the objects would be quiet, yet their motion would still testify to the galaxy's flow. The mysterious part is that the stage itself is alive. The disk rotates, the tide stretches, and the nearby stars reshuffle the map while we try to read it, as if the coordinate grid were drawn on flowing water. The more carefully we define position, the more we notice that position is always embedded in change. That is the tension we carry into the next chapter. We have the coordinate system, the dominant vectors, and the sources of uncertainty, and we have a way to separate what is robust from what is contingent. The robust part is the scale of motion, while the contingent part is the exact set of encounters that may sculpt the path. Now we attempt the headline calculation, where specifically do Voyager 1 and Voyager 2 end up in 1,000,000 years, and which stars might they pass on the way? The question is not only about distance, but about context. What neighborhood surrounds them when the solar system has moved on? The dark between stars is not empty, and it is not still. The question is not whether Voyager will die, but where it will be when our era is a footnote, and what moving lights will surround it when it drifts through the future sky. And beneath that is a quieter question. When the map changes, what does it mean to say we know where anything is? Now we attempt the headline calculation. Where Voyager 1 and Voyager 2 end up after 1 million years depends on frames, uncertainties, and a galaxy that refuses to hold still. The arithmetic looks clean on paper, yet the meaning of where changes. Once the sun itself becomes a moving reference point. In a sense, we are predicting not a destination, but a relationship. Two drifting objects whose separation evolves inside a much larger flow. Start with the simplest piece. Distance traveled is speed, times time, measured against the sun as a moving origin. In that sun-centered frame, we treat the probes as coasting bodies whose engines are long silent and whose remaining motion is essentially inertial. The word coasting sounds casual, yet it describes a regime where momentum dominates and forces are sparse. Voyager 1's asymptotic speed is about 17 kilometers per second in the sun frame. Voyager 2's is about 15 kilometers per second, with small updates as tracking improves. Asymptotic matters here. It means the speed after the last significant planetary gravity assists have faded into a steady outbound cruise. Past that point, the trajectory is mostly a straight line, with only gentle curvature from distant gravity. Those numbers are not guesses pulled from a press release. They come from decades of radiometric tracking, Doppler shifts, and careful orbit determination, where tiny frequency changes in a radio carrier reveal velocity to exquisite precision. The Deep Space Network listens for a tone that returns slightly higher or lower, and that shift encodes speed along the line of sight. Range measurements, timing, and Earth's own motion are folded in, so the final velocity is a solved puzzle, not a single reading. Even so, the solution depends on which center you choose: heliocentric, barycentric, or a more formal solar system ephemeris frame. The barycenter is the solar system's true balance point, and it wanders as Jupiter and Saturn tug the sun around. That wobble is small in distance, yet it matters when you are trying to define straight over 1 million years. The frame is the stage, and the stage itself can move. Convert to units that match the solar system. One astronomical unit is the Earth, sun distance, and it becomes our ruler. It is a human-scale unit in an inhuman setting, anchored to the orbit that taught us what 1 year means. The AU also carries history. Astronomers once argued over its value because it set the scale of everything beyond Earth. 17 kilometers per second is about 3.6 AU per year. Using 1 AU per year, near 4.74 kilometers per second. That conversion is approximate, yet it is stable enough for million-year scale. It also hides a quiet fact. We are turning a spacecraft's speed into a fraction of Earth's orbital yardstick. The probes are leaving on a pace measured by the planet they departed. 15 kilometers per second is about 3.1 AU per year by the same conversion. These are rounded values, and they depend on whether we quote heliocentric or barycentric solutions. The difference is subtle, but over 1 million years, even subtle bookkeeping choices can become visible in the last digit. A small change in speed, sustained for geological time, becomes a measurable change in distance. Multiply by 1 million years. Voyager 1 covers roughly 3.6 million AU in that time, while Voyager 2 covers roughly 3.1 million AU. On screen, the numbers feel almost absurd. Millions of Earth. Sun distances, stacked end to end like a ruler that never stops unfolding. The camera can pull back and back, yet the tick marks keep arriving. Now convert AU to light years. 1 light year is about 63,241 AU, so the division turns millions into tens. This is where the scale snaps into focus, because light years are the unit our imagination reserves for stars. It is also a reminder that we are converting a speed into a time of light measure, as if distance were something a signal could traverse. Voyager 1's 3.6 million AU becomes about 57 light years from the Sun after 1 million years. Voyager 2's 3.1 million AU becomes about 49 light years from the Sun. The difference between them is not dramatic in galactic terms, yet it is still the width of a small stellar neighborhood. A few dozen light years can contain many suns, many planets, and many unknown histories. These numbers deliver the promise, but they also set a trap. They sound like absolute destinations, even though they are only separations from a moving star. From the Sun is a phrase that smuggles in a frame, and frames are the hidden machinery of every long-range prediction. If the origin moves, the meaning of away changes with it. The Sun is not parked. Over the same million years, the Sun carries the entire solar system about 230 light years along its galactic orbit. That motion is not a straight sprint across a static backdrop, but a curved path around the Milky Way's center, embedded in a disk that rotates and ripples. In a wide visualization, the Sun's track looks like a slow arc, and the probes ride as small offsets on its edge. That 230 light years is the background translation in a galactic frame. It is larger than Voyager's Sun relative drift, which is why the probes are offsets on a much longer arc. If you draw the Sun's future track as a sweeping ribbon, Voyager's million-year journey becomes a smaller thread stitched alongside it. The thread is real, but it is not the whole tapestry. So we split the question into 2 coordinates. There is the probe's distance from the Sun, and there is the probe's position in the Milky Way. The first is a clean, almost classroom calculation, while the second is a choreography of many moving parts. One is arithmetic, and the other is celestial mechanics performed by an entire disk of stars. In the Sun frame, the answer is tens of light years outward along a fixed departure vector. In the galactic frame, the answer is the Sun's future location plus that vector. The same spacecraft can be 57 light years away and still be traveling through roughly the same region of the galaxy as its birthplace. The probe is not escaping the neighborhood of the Sun's orbit so much as drifting within it. This is the core bookkeeping. Galactic position equals the Sun's future position plus Voyager's heliocentric displacement, with tides and encounters adding slow curvature and rare kinks. The elegance is deceptive because every term in that sum carries its own uncertainty budget. A tidy equation can still describe a messy universe. That framing also explains why the sky directions we quote today are temporary. Voyager 1 is described as heading toward Ophiuchus, and Voyager 2 toward Sagittarius, but those are present-day labels. They are the names we use because we can point a camera at the sky today and draw familiar lines. The labels are convenient, not fundamental. Constellations are not objects. They are alignments that dissolve when stars move, and 1 million years is enough time for the pattern to break. What looks like a coherent figure is really a set of unrelated distances layered along the line of sight. The sky is a collage, and time peels the layers apart. Proper motion is the mechanism. Nearby stars shift across the sky because they have their own velocities. often tens of kilometers per second relative to the sun. The sky is not a dome. It is a depth-filled volume, and the nearest points slide fastest. When we speed up the footage, the bright points drift like snow in a headlight beam. Over 1 million years, tens of kilometers per second becomes tens of light years of displacement. The background that defines Ophiuchus and Sagittarius will be rearranged beyond recognition. Some stars will drift out of those outlines, while others will drift in, creating new accidental pictures. If a future observer tried to trace our constellations, they would be drawing ghosts. So the probes do not fly through a fixed mural. They fly through a star field that is itself flowing, with every point carrying its own trajectory. The Milky Way is less like a museum and more like a river, where every current has a slightly different speed. The riverbed is gravity, and the water is everything that moves within it. To describe a million-year sky location, we must choose a coordinate system that survives the rearrangement. Galactic longitude and latitude are more stable than constellations, but even they ride on a changing potential. The galaxy's gravity is not a perfect sphere, and its disk is not a perfectly smooth sheet. Spiral structure, clumps, and dark matter all shape the background field. In practice, we propagate a state vector. We start with today's best position and velocity, then integrate forward through a model of the Milky Way's gravitational field. The state vector is a compact statement of where and how fast, but it must be carried through time by physics. The computer does not guess. It steps forward moment by moment and lets gravity do the writing. The integration is not a single line. It is a cloud of solutions because every input has uncertainty, and every uncertainty expands with time. When you watch the visualization, the trajectory is not a hairline. It is a translucent plume. The plume is the honest picture of prediction. Distance uncertainty stays relatively narrow because speed is well measured and changes slowly. Direction uncertainty grows faster because tiny angular errors become huge lateral offsets after tens of light years. The farther you project, the more a small pointing ambiguity becomes a wide corridor. In a long pullback shot, the corridor looks like a cone of pale light. A 1-degree error sounds small on a sky map. After 57 light years, it becomes about 1 light year of sideways displacement, and smaller errors still matter. In a region where stars are separated by only a few light years, that sideways drift can decide which neighborhoods the probe even passes near. The difference between near and not even close can be a fraction of a degree. Then add model uncertainty. The galactic tide is smooth in first approximation, but local structure and epicyclic motion add slow deviations that accumulate. The sun itself does not follow a perfect circle. It oscillates radially and bobbles above and below the galactic plane. Those motions are modest, yet they change the reference flow the probes ride within. Those oscillations are gentle, yet they matter for long integrations. A changing vertical position slightly changes local stellar density, which slightly changes encounter probabilities, which slightly changes the distribution of possible future paths. The chain is subtle, but over 1 million years, subtle chains can become visible. In a statistical sense, the environment breathes as the sun rises and falls through the disk. Then add the hardest term. Passing stars create intermittent gravitational kicks, and the timing and geometry are sensitive to initial conditions. Each encounter is a small nudge in a vast room, but the order of nudges matters. A sequence of tiny deflections can add up, not in speed, but in direction. This is where modern catalogs enter the story. Gaia measures positions, distances, and proper motions for over 1 billion stars, tightening near-term encounter forecasts. It turns the sky from a painted ceiling into a measured 3D map with velocities attached. Historically, this is a revolution. Earlier generations had star positions, but not the full choreography. Even with Gaia, predictions degrade with time. Uncertainties in stellar radial velocities and small gravitational interactions compound, widening the corridor of possible close approaches. A star's sideways motion is often well known, while its motion toward or away from us is harder, and that missing piece is decisive. Without the radial component, the future is a depth blur. So we do not promise a single flyby list for 1 million years. We promise a probability distribution of encounters, with confidence dropping as the clock runs forward. The future becomes a set of weighted possibilities, rather than a single scripted itinerary. The map becomes less like a route and more like weather. Still, we can explain what a predicted encounter looks like. Voyager 1 is often cited to pass within a few light years of Gliese 445 in about 40,000 years. In visuals, you can imagine 2 lines in space that never meet, yet come close enough to feel like a brush of passing shadows. The star is not a target, but it becomes a reference marker for scale. That example is not a prophecy. It is a template for scale, showing that close in interstellar terms can still mean several light years. In a city, that would be a neighboring street, but in space, it is a gulf containing trillions of kilometers. Even the nearest pass is still mostly emptiness. A few light years is close enough to mention, yet far enough to be dynamically gentle. The gravitational deflection from such a pass is negligible for a fast, unpowered probe. Gravity falls off with distance, and at multi-light-year separations, the pull is more suggestion than command. The probe feels a whisper, not a hand. Deflection depends on impact parameter and relative speed. With multi-light-year distances and tens of kilometers per second relative motion, the bending angle is tiny. The probe's path is not aimed by the star. It is barely perturbed, like a fast pebble passing a distant hill. The hill is massive, but the miss distance is too large. Only extremely close stellar encounters would significantly alter course. Those are rare, but not impossible over million-year windows in a crowded disk. A single unusually close pass could rotate the trajectory enough to shift the far future sky region by many degrees. The question is not whether such a pass can happen, but how often it should be expected. The same logic applies to capture. For a star to capture Voyager, the probe must lose energy relative to that star, which requires a 3-body interaction or an exceptionally close, slow encounter. Capture is not just proximity. It is a specific energy bookkeeping problem. Without a mechanism to shed energy, the probe simply flies through. Most encounters are flybys, not captures. The probes remain interstellar drifters, with trajectories that are stable in speed and only slowly rotated in direction. Their motion is dominated by the momentum they carried out of the planetary era. That momentum is the lasting gift of the gravity assists that launched them. That stability raises another question viewers carry. Does interstellar space slow them down, like air resistance in a thin fog? The intuition is understandable, because on Earth, even a thin atmosphere eventually wins. We are trained by friction to expect motion to fade. The interstellar medium is too thin to matter. Typical densities near the Sun are fractions of a particle per cubic centimeter, which is effectively nothing for macroscopic drag. Put differently, a laboratory vacuum is dense compared to the space between stars. The probes move through a medium so sparse it barely qualifies as a gas. Even at 15 to 17 kilometers per second, the momentum exchange with that sparse gas is negligible. Over 1 million years, the speed loss is far smaller than our measurement uncertainties. The probes are not carving a wake, they are slipping through a near emptiness. If you could see the particles, they would look like isolated sparks in a vast dark. Dust impacts do occur, but they do not act like a break in the usual sense. They pit surfaces and add tiny random impulses, yet the net deceleration averages near zero. Over long times, the effect is more like microscopic sandblasting than aerodynamic drag. The spacecraft age by erosion, not by slowing, so the million-year distance estimate remains dominated by inertia. The probes coast because space is not empty, but it is empty enough. That emptiness is part of the eerie calm of deep space footage. No wind, no flutter, only steady motion. The silence is physical, not just emotional. Now we return to the moving frame problem. In the galaxy's frame, the Sun advances about 230 light-years, and Voyager's offset is added on top. The spacecraft are not escaping the galaxy. They are embedded in its rotation like leaves carried downstream. Their paths are local deviations on a much larger current. That means Voyager 1 is not simply 57 light-years from where it started. It is roughly 57 light-years from the Sun's future position, which itself is far from today's Sun. If you freeze the galaxy at the present, you misunderstand the entire geometry. The correct picture is a moving origin, traced through a moving field. So the probe's galactic coordinates are best described as offsets from a future Sun. They trail or lead that future Sun, depending on vector geometry, not on any cosmic notion of outward. Outward is a word that belongs to a local map, not a galactic one. In the Milky Way, there is motion, not a simple edge. This is where the narrative becomes mysterious again. We can compute a distance with confidence, yet the direction becomes a widening cone. The farther we project, the more the future resembles a spotlight beam that spreads. The beam is narrow at the source and broad at the horizon. The cone of futures is narrow in radius and wide in pointing. It is shaped by tracking uncertainty, by tiny non-gravitational forces, and by the unknown sequence of stellar nudges. Even a minuscule acceleration, applied unknowably over long spans, can tilt a trajectory in a way that matters. Over 1 million years, a whisper can become a turn. For Voyager 1, the cone extends to about 57 light-years in the Sun frame after 1 million years. For Voyager 2, it extends to about 49 light-years, with a similar widening in direction. In a visualization, the endpoints are not dots, they are soft-edged regions. The softness is the signature of time. Within each cone, there are corridors of higher probability. Those corridors reflect our best-fit velocity vectors today, and the fact that most perturbations are small. The most likely futures cluster around the straight line extrapolation, but they never collapse to a single line. The corridor is a best estimate, not a guarantee. But the corridor is not a promise. Over 1,000,000 years, a single unusually close encounter could rotate the vector enough to shift the sky location by many degrees. The probability is low, yet the consequence is large, which is why it cannot be ignored. Rare events are the tax we pay for long timelines. That is why we talk about sky regions, not sky points. Toward Ophiuchus and toward Sagittarius become historical footnotes, not reliable signposts. They are the language of the launch era, not the language of the 1,000,000-year forecast. The probes will outlive our sky stories. We can still say something meaningful about the likely neighborhoods. At tens of light years from the Sun, the probes remain within the local stellar volume, not the far galaxy. They are not crossing spiral arms or diving into the galactic center. They are drifting through a familiar density regime. The environment is interstellar, yet not exotic by Milky Way standards. That volume contains hundreds of stars within 50 light years today, and many more by the time the Sun has moved 230 light years along its orbit. The count changes because the neighborhood is not a fixed bubble. It is a shifting sample of the disk. The Sun's future surroundings will be drawn from a different part of the galactic stream. The local neighborhood itself will be different. Some stars now far away will drift closer, and some familiar nearby stars will have moved on. The nearest stars. List in 1,000,000 years will be a different cast, even if the physics is the same. The stage changes, even when the rules do not. So the path is not a line through today's catalog. It is a line through the future phase space of the disk, where every star has advanced along its own orbit. When we say Voyager passes near a star, we mean a future star in a future place, not a static landmark. The encounter is an appointment both parties are moving toward. This is why encounter prediction is a living calculation. As Gaia improves and future surveys extend baselines, the near-term part of the corridor sharpens. A longer observation arc turns uncertain velocities into measured ones, and measured ones into better forecasts. The first tens of thousands of years become clearer, even as the 1,000,000-year end remains hazy. But the 1,000,000-year horizon remains probabilistic. The galaxy's complexity turns exact answers into distributions, even when the underlying physics is deterministic. Determinism is not the same as predictability, especially in a crowded gravitational environment. The equations are strict, yet the inputs are never perfect. We can make that tension explicit. The probes are simple objects, yet their long-term context is a chaotic crowd. A gold-plated record and a radioisotope-powered chassis become, over time, test particles in a living galactic disk. Their cultural weight is enormous, yet their dynamics are humble. We can also restate what does not change. The probes do not stop, and they do not spiral into darkness under drag because the medium is too thin. Their motion is the purest kind of continuation, a lesson in inertia written across interstellar space. They are still obeying the same physics that launched a stone from a hand. They also do not get dramatically slingshotted by typical stellar passes. Gravity is strong up close, but a few light years is still far. The romantic idea of a star grabbing the probe is usually defeated by distance and speed. Most of the time, the stars are spectators, not actors. So the baseline story survives. Voyager 1 ends up roughly 57 light years from the Sun after 1,000,000 years, and Voyager 2 ends up roughly 49 light years. Those are separations, not addresses, but they are still meaningful scales. They tell us how far a human-made artifact can drift on stored momentum alone. Then the galactic story overlays it. Both probes are carried roughly 230 light-years along with the Sun, so their absolute galactic positions are near the Sun's future orbit track. In a wide shot of the Milky Way, they remain close companions to the solar system's long arc. The probes are not lone arrows in space, but small offsets in a moving system. In other words, they are not racing away from the Milky Way. They are drifting within it, separated from a moving home by tens of light years. The galaxy remains their ocean, and the Sun remains a moving buoy they slowly leave behind. The buoy keeps traveling, and the gap keeps widening. That separation is the scale of the message's exile. The golden record becomes not a beacon, but a relic moving through a changing neighborhood. Its intended audience was always hypothetical, and 1,000,000 years makes that hypothesis feel both grander and stranger. What does it mean to send a message when the address is a probability cloud, and the neighborhood is the point? In 1,000,000 years, the star field around Voyager will not match any sky chart we recognize. The familiar constellations will have loosened, and the bright stars will have traded places in subtle, irreversible ways. The night sky itself will have a different personality. We can compute a distance, and we can sketch a corridor, but we cannot name the exact stars that will frame it. The galaxy keeps its secrets by staying in motion. Even our best maps are snapshots, and the snapshot is already aging. The moment we print the chart, the universe has moved on. This chapter's calculation is therefore both a promise and a warning. The numbers are real, yet the map they sit on is alive. Precision in one dimension does not guarantee certainty in all the others. A clean distance can coexist with a blurred direction. After we plot these corridors, the question deepens. What can destroy, capture, or erase Voyager over such a long time, when probability finally beats planning? That is the next threshold. Once we know where Voyager is likely to be, we have to ask what can happen to it there. And that question lingers because it is not only about spacecraft. It is about how the universe treats small artifacts over immense spans, and about whether any message can remain intact long enough to be found. We have a corridor of likely positions after 1,000,000 years, drawn from inertia and moving frames. Now we ask what could interrupt that corridor, because empty space still has teeth. On a star map, the path looks clean and geometric, yet the medium between stars is not truly empty. It is thin, cold, and restless, filled with particles, fields, and the long reach of gravity. Voyager is already becoming a different kind of object, and that shift is easy to miss. It is no longer a mission with telemetry and commands, but a drifting artifact exposed to the interstellar medium. The question is not whether it stops, because nothing is waiting to break it. The question is what slowly edits it, line by line, until the original machine becomes a different physical document. Start with the most common hazard, because it is also the quietest. Micrometeoroids and interstellar dust grains are sparse, yet the path length is enormous. Over 1,000,000 years, even a thin fog becomes a sandblaster, and even rare hits become a steady statistical certainty. The violence is not loud, and it is not fast, but it accumulates with a patience that machines cannot negotiate. In the local interstellar medium, gas densities are fractions of a particle per cubic centimeter, and that number itself hides complexity. The gas is mostly hydrogen and helium, with traces of heavier atoms, and it is partially ionized by ultraviolet starlight. Dust is far rarer than gas, but grains carry mass and momentum, and their chemistry can be surprisingly rich. A grain can be silicate, carbonaceous soot, or an icy composite, and its density determines how much damage it does. A grain at tens of kilometers per second hits like a microscopic bullet because kinetic energy scales with velocity squared. At those speeds, even a speck can behave like a hypervelocity projectile, briefly generating shock, heat, and a spray of ejecta. In a lab, such impacts leave tiny craters with raised lips and fractured halos, and the same physics applies here. The spacecraft does not feel a single impact the way we do. It experiences a long, granular weather. Cumulative impacts are a statistics problem, not a single dramatic event, and that makes them easy to underestimate. Voyager 1 travels roughly 57 light-years relative to the Sun in 1,000,000 years, which is an almost absurd lever arm. Multiply that distance by its cross-sectional area, then fold in uncertain dust density and grain sizes, and the uncertainty becomes part of the story. We are not counting pebbles on a road. We are estimating collisions in a medium we can only sample indirectly. The result is not a clean number, but a range of expected hits, and the range matters as much as the average. Many impacts are sub-millimeter grains that leave pits, craters, and spall marks, like a surface slowly stippled by invisible hail. A few are larger grains that can gouge deeper, though they remain unlikely, and their rarity is precisely why they are hard to model. Over 1,000,000 years, the tail of the distribution begins to matter, because long time gives rare sizes a chance to appear. Surface abrasion matters because it changes the spacecraft's skin, and the skin is not just cosmetic. Paints and thermal blankets can be peppered and darkened, which changes how they absorb sunlight and radiate heat. Even in interstellar space, where sunlight is faint, thermal balance still matters for material stress and brittleness. A surface that darkens can cycle differently when it passes through varying radiation environments, and that cycling can open micro cracks. Edges and protrusions take more damage because geometry concentrates exposure and because impacts are not evenly distributed. A flat panel presents a broad target, but a sharp corner can catch particles from more angles as the attitude changes. Antennas, booms, and instrument housings act like leading edges on an aircraft. Except the air is a near vacuum filled with fast grains. Over long spans, the leading edges become rounded, and the spacecraft's silhouette slowly softens. Shielding is not armor in the cinematic sense, but it still matters, and it matters in subtle ways. The high-gain antenna dish can shadow parts of the bus, creating a protected sector that sees fewer direct hits. That shadow is not absolute, because grains arrive from a distribution of directions, and some ejecta can ricochet. Still, even partial shadowing changes the pattern of wear, leaving a faint map of orientation written into the metal. The RTG booms and instrument booms present thin targets, and their orientation changes as attitude control fades. In the operational era, Voyager maintained a stable pointing geometry, and that stability concentrated exposure on predictable faces. Once power is gone, the spacecraft may tumble slowly, driven by tiny torques and the uneven push of radiation. Tumbling spreads the damage across more surfaces, reducing deep wear in one spot, and it also exposes delicate areas that were once kept in shadow. There is a visual here that is easy to imagine, because it resembles aging on Earth, only without air or water. The gold-colored thermal blankets become dull, then mottled, then peppered with pinprick craters. The aluminum skin loses its crisp sheen, and the dish becomes a pale, scarred bowl against a black star field. In close-up, every crater has a rim and a spray pattern, like frozen fireworks. Catastrophic collisions are improbable, but never impossible, and that distinction matters in deep time. A centimeter-scale object could puncture, fracture, or sever a boom, and the immediate effect would be mechanical rather than thermal. A larger rock would be devastating, yet the density of such bodies in interstellar space is extremely low. Interstellar objects exist, as we have now seen with visitors like Oumuamua and Borisov, but the volume between stars is so vast that exists does not mean likely to hit. So the dominant dust story is not destruction, but erosion, the slow conversion of a manufactured surface into a weathered one. Over 1 million years, the probe becomes pitted and matte, and its reflective highlights fade into a uniform gray. Its sharp edges soften, and its surfaces record a long, random hail of impacts that never stops. If you could run a finger across it, you would not feel smooth paint. You would feel a fine, hard roughness like sandpaper. Dust also delivers tiny momentum kicks, but they do not act like ordinary drag, and that point is important. The impulses are random in direction and average out in speed, because the probe is not plowing through a dense gas. The main effect is a slow, random walk in attitude and micro-perturbations in trajectory, like a billiard ball nudged by invisible taps. Over 1 million years, those taps can slightly widen the corridor of possible positions, even if they cannot meaningfully slow the craft. Radiation is the second slow violence, and it is more uniform than dust, because it arrives from many directions. Galactic cosmic rays penetrate deeply, while UV and charged particles work on exposed surfaces, and each does a different kind of damage. Cosmic rays are mostly high-energy protons and heavier nuclei accelerated by supernova remnants and other energetic events. They are rare compared to sunlight, yet their energies are extreme, and they can punch through centimeters of material. The spacecraft becomes a test coupon for 1 million years of space weather, and the term weather is not metaphorical. Radiation dose accumulates, and dose is what matters for chemistry and structure, not the drama of a single event. Cosmic rays break chemical bonds and create lattice defects, leaving behind a trail of ionization and displaced atoms. Plastics embrittle and crack, adhesives lose strength, and insulation becomes brittle, which is a quiet failure mode that looks like aging rather than damage. Metals survive better, but their surfaces can darken and sputter under particle bombardment, and their microstructure can change. Aluminum can develop a roughened oxide layer, and thin coatings can be gradually eroded. In vacuum, there is no rust, but there is still chemistry driven by radiation and by implanted ions. The result is a surface that is chemically altered, not corroded in the terrestrial sense, and that distinction is easy to forget. Electronics do not fail in the usual operational sense, because they will already be unpowered, and the mission's death is not a switch flipping. They become inert fossils of silicon and solder, vulnerable to long-term radiation damage, but irrelevant to function. Over time, semiconductor junctions accumulate defects, and insulating layers trap charge, and tiny structures become less like circuits and more like mineral inclusions. The probe's death is not a moment, but a transition into archaeology, where the object remains, but the purpose is gone. That archaeological framing has a history behind it, because Voyager was designed with longevity in mind. In the 1970s, engineers built for the known hazards of the heliosphere, and they did so with conservative margins and redundant systems. They did not design for 1,000,000 years of interstellar exposure, yet the materials they chose carry their own deep time behaviors. The spacecraft is both a product of its era and a participant in a timescale that its builders could only imagine. The golden record is the cultural heart of the spacecraft, and it is also a materials problem with very specific constraints. The record is gold-plated copper, chosen for corrosion resistance and stability, and because gold is chemically inert in most environments, its cover is aluminum, designed as a shield against micrometeoroids and radiation, and also as a physical frame for the etched instructions. The message was never meant to be broadcast. It was meant to be found, handled, and decoded. The cover is not perfect protection, but it is a deliberate one, and deliberate choices matter over long spans. It reduces direct abrasion and blocks some UV, and it also limits how many particles can strike the record at shallow angles. It carries the etched decoding diagrams, which must remain legible for the message to remain recoverable. Those diagrams are not decoration. They are a compact attempt to bridge biology, culture, and physics using geometry. Over 1,000,000 years, pitting could scar the cover and record surface, and the scars would not be evenly distributed. The question is whether the grooves remain readable, not whether the object remains intact, because a scratched record can still play. Even partial damage could still leave enough signal for reconstruction if anyone knows how to listen and has the patience to infer missing parts. The record's design anticipates this by using physical geometry, not ink, as the information carrier. And that choice is a bet on physics over language. Radiation also changes optics and contrast, and that affects the diagrams as much as the music. Surfaces darken, and fine markings lose crispness, especially where microcraters blur edges and create glare. Yet the etching is deep compared to a thin printed layer, and depth is a kind of redundancy. It is a small engineering lesson hidden inside a cultural artifact. If you want a message to last, carve it. Then there is charging, a hazard that sounds dramatic but usually is not, and the difference between drama and reality matters here. In plasma, surfaces accumulate charge depending on sunlight, particle flux, and material properties, and different materials can charge differently. With power gone, arcing becomes far less likely, because there is no energized circuitry and no high-voltage supply feeding a discharge. The spacecraft is mostly a passive conductor and insulator assembly, drifting through a dilute ionized gas. Yet surface potentials can still build and discharge locally, especially across insulating patches and sharp edges. Small discharges can pit surfaces and degrade coatings, leaving tiny burn marks that resemble impact scars. Charging also influences how dust grains stick or bounce, subtly changing contamination patterns over deep time. A charged surface can electrostatically attract fine particles, so some areas may accumulate a faint dusting while others stay cleaner. Sputtering is the more persistent effect, and it is almost the definition of slow violence. Energetic ions knock atoms off exposed surfaces, atom by atom, and the loss is measured in nanometers over long spans. Over 1 million years, sputtering can thin coatings and alter thermal properties, though it rarely threatens structural integrity. It is less like a hammer and more like a file, and the file never gets tired. These are the ordinary hazards, and they are relentless because they do not need a special event to begin. They do not create a single cinematic failure, and they do not offer a clean ending. They turn the spacecraft into an increasingly weathered object, still moving, still intact, but slowly rewritten. If you could compare it to launch day photographs, the difference would feel like time made visible. Now the story shifts from materials to gravity, because gravity can change the path itself, and a path is a kind of fate. The most dramatic fate would be capture by another star, which sounds like a homecoming but is really a mathematical trap. That requires more than a close pass, because capture is an energy problem, not a proximity problem. To be captured, Voyager must lose enough kinetic energy relative to the star that its trajectory closes into an orbit. A lone star cannot easily capture a fast interstellar object, and this is a counterintuitive point. Voyager approaches with a relative velocity that is typically tens of kilometers per second in the local stellar frame, and that speed is stubborn. To become bound, it must leave the encounter with less than the star's escape speed at that distance, which is a strict threshold. If it leaves faster than escape speed, it is still on an open hyperbola, no matter how close the pass looked. Escape speed falls with distance, and at light-year scales it is tiny, far smaller than Voyager's cruising speed. So capture demands an extremely close pass, or an unusually low relative velocity, or a three-body interaction that can exchange energy. In practice, that means passing through a star system where planets or a binary companion can steal energy, like a gravitational pickpocket. Without that extra body, gravity bends the path but returns the energy, and the probe departs with essentially the same speed. Gravitational focusing increases the chance of a closer approach because a star's gravity bends trajectories inward, and that bending changes the effective target size. But focusing is limited when the incoming speed is high, because the encounter time is short. The faster Voyager is relative to the star, the less time gravity has to turn it, and the smaller the deflection angle. In the extreme, the star becomes just another waypoint, adding a slight curve to a nearly straight line. So, the capture scenario is possible, but it is a lottery with strict rules, and strict rules keep the odds small. The impact parameter must be small, and the velocity must be favorable, and the geometry must align with a helpful third body. Over 1 million years, the probability is low, yet not zero, because time makes rare geometry eventually occur. This is one of the unsettling truths of celestial mechanics. Improbability is not impossibility when the clock runs long enough. Most stellar encounters are flybys measured in light years, not astronomical units, and that scale difference changes everything. At those distances, the deflection angle is tiny, and the star's gravity is more like a gentle suggestion than a grab. The trajectory corridor widens, but it does not usually kink sharply, and the probe continues outward. Even so, the cumulative effect of many tiny deflections can slightly reshape the corridor, like a river that meanders without ever turning into a waterfall. Still, a single unusually close passage could dominate the story, and dominance is what rare events do. A pass within thousands of AU could rotate the outbound direction by a measurable amount, even if the speed barely changes. Over the remaining distance, that small rotation becomes light years of lateral shift, and the corridor slides across the background stars. The probe's future position is not just a matter of speed, but of angle, and angle is where gravity leaves its fingerprints. Now add a different kind of environment, denser regions of the interstellar medium, because not all space has the same texture. The solar system moves through a patchy galaxy, and some patches are molecular clouds, where gas is cold enough for molecules to survive. These clouds are dusty and far denser than the local interstellar medium, and they are the nurseries where stars form. Entering one would be like moving from a high desert into a fog bank, except the fog is made of hydrogen, carbon monoxide, and dust. If the sun passed through a cloud, dust density would rise dramatically, and the change would be physical, not just conceptual. Erosion rates would increase, and the probability of larger grain impacts would rise because the size distribution shifts and the number of grains rises. The probes would not slow much, because even a cloud is still extremely tenuous by Earth standards, but they would be sand-blasted harder. The spacecraft's surface would record that passage as a distinct layer of damage, like a tree ring written in craters. Over 1 million years, the chance of entering a dense molecular cloud is low, and the geometry of the local neighborhood supports that. The nearest giant clouds occupy small fractions of volume, and the sun's path is not aimed at a known one on that timescale. But smaller cloudlets and denser filaments are plausible, and they are harder to map, especially when they are cold and dark. The galaxy is not a uniform sea. It is a structured medium with hidden gradients. So we treat clouds as a credible but unlikely amplifier, a scenario that steepens the wear curve without changing the basic physics. They do not rewrite the baseline, but they can compress 1 million years of gentle abrasion into a shorter, harsher interval. In a cloud, the slow violence becomes less slow, and the probe's surface would show it. The question becomes not whether Voyager survives, but how legible its details remain after an encounter with denser dust. The solar system's own far future adds another layer of tension, because the sun does not travel alone through a static galaxy. The Oort cloud is weakly bound and easily perturbed by passing stars and the galactic tide, and tide here means the combined gravitational pull of the Milky Way's mass distribution. Over long spans, those perturbations stir comets and reshape the outer reservoir, changing which objects are sent inward and which are ejected. The outer solar system is not a quiet shell, but a dynamic borderland where small nudges accumulate into rearrangements. Voyager is not part of the Oort cloud, because it is unbound and on a different trajectory, and that distinction is crucial. But the same passing stars that stir comets also define the gravitational weather around the sun, and that weather is part of Voyager's context. A close stellar pass can trigger comet showers inward long after the encounter, because the Oort cloud responds slowly. That is a separate story from Voyager's drift, yet it frames the million-year future as active, not frozen. Even far from planets, gravity keeps rearranging the inventory, and that rearrangement is the background to every long trajectory. The sun's gravity fades with distance, but it does not vanish, and the galaxy's tidal field never truly turns off. The probe remains a small mass moving through a field of larger masses, and the field is structured by tides and encounters, not by friction. This is why it keeps going. There is no interstellar break, only interstellar geometry. Now we turn the hazard question back toward us, because the most dramatic intervention could be human, and that possibility changes the tone. If humanity persists, retrieval is not physically impossible, and physics is the easy part. It is a question of will, capability, and whether the probe remains worth chasing after centuries of other priorities. The idea feels like science fiction, yet it is also a straightforward pursuit problem. Match position, match velocity, and survive the long transit. An intercept in interstellar space is a navigation and propulsion challenge, because the target is small and the distances are unforgiving. You must match a trajectory with a target moving at tens of kilometers per second, and you must do it with limited opportunities for correction. Over centuries, advanced propulsion and autonomous navigation could make it feasible, even if it remains expensive. The intercept craft would need exquisite astrometry, robust guidance, and a way to slow down relative to the probe, because a flyby at those speeds would be a blink. If humans do not persist, the probes become unclaimed objects, and their meaning becomes hypothetical. Their message becomes a sealed letter drifting through a city with no inhabitants, perfectly intact and perfectly unread. The same trajectory can be a triumph or a relic, depending on whether a future mind exists to care. That mirror is part of the mission's design, even if it was never stated so bluntly. This mirror sharpens the chapter's tension because it forces two timescales into the same frame. On human timescales, Voyager is nearly indestructible because space is sparse and the structure is robust, and because there are few immediate threats. On cosmic timescales, it is fragile because everything is eventually abraded, irradiated, and perturbed, and because small probabilities become real. The probe survives by coasting, but it also survives by being lucky, and luck is not a strategy. Time is the ultimate environment because it multiplies small probabilities into real outcomes and turns whispers into forces. 1,000,000 years is long enough for slow erosion to matter, and long enough for radiation dose to rewrite polymers and coatings. It is also long enough for rare gravitational geometry to become plausible, even if it remains unlikely. When we say 1,000,000 years, we are really saying enough time for the improbable to knock on the door. So what could stop them is not one villain, but a menu of slow processes that never need permission to begin. Dust pits the skin, radiation ages the materials, plasma charges the surfaces, and gravity keeps open the possibility of a sharp turn. The probes survive by coasting through a sparse medium, yet they also survive by avoiding the rare dense patch and the rare close encounter. Their endurance is real, but it is not absolute. We end with the most unsettling realization because it is not about metal or math. Even if Voyager remains intact, its message can become unreadable without a reader, and unreadable is a kind of erasure. Coordinates and trajectories matter only if someone is there to interpret them, and interpretation is not guaranteed by physics. The golden record is durable, but meaning is not a material property. With the physical fate explored, we return to meaning. Where will Voyager be in 1,000,000 years? And what does it matter if no one is there to listen? The probe will still be moving through the dark, carrying a carved attempt at contact, while the universe decides whether contact is ever made. We return to the headline question, with the math finally allowed to speak clearly. After 1 million years, Voyager 1 is best estimated about 55 to 60 light-years from the Sun. Voyager 2 is best estimated about 45 to 55 light-years from the Sun. Those ranges reflect frame choices, tracking uncertainty, and long-term gravitational weather. They also reflect something easy to forget. Space is not a grid painted onto reality, but a set of measurements tied to motion. The clean core is still linear drift, and it is almost embarrassingly simple. Voyager 1 coasts near 17 kilometers per second, which is roughly 0.00057 light-years per year. Multiply by 1 million years, and the separation lands near the high 50s, even before we argue about the fine print. Voyager 2 coasts near 15 kilometers per second, so its million-year separation lands near the high 40s. In both cases, the probes are moving far below the speed of light, yet deep time makes even slow motion accumulate into interstellar distance. The numbers are not a destination, they are a distance from a moving origin. The Sun is not a pin in space, and neither is the solar system's barycenter. Even the term "from the Sun" hides a practical choice. Do we measure from the Sun's center, the system's center of mass, or a future ephemeris that no longer has planets in the same places? In a million years, the inner planets will have completed millions of orbits, and the outer planets tens of thousands. The probes will not care, but our bookkeeping will. Now we widen the frame, because the Sun is not waiting in place. Over the same million years, the solar system moves about 230 light-years along its Milky Way orbit. That motion dominates the absolute galactic displacement, while Voyager adds a smaller offset vector. In the galactocentric view, the probes are not leaving the galaxy. They are trailing a migrating solar system. They remain inside the thin disk, embedded in the same rotating stellar stream that carries gas, dust, and stars around the center. Picture the visual. A vast, dim, spiral lane of the Milky Way, with the Sun's track drawn as a long, glowing arc. Against that arc, Voyager 1 and Voyager 2 are tiny sparks, offset by only a few dozen light-years, like flecks of ash drifting beside a moving train. The offset is real, but it is modest compared with the solar system's own journey. The probes are not arrows fired into emptiness. They are crumbs falling from a moving table. So where are they in the galaxy? They are not in a fixed constellation, because constellations dissolve on million-year timescales. Their best description is relational and kinematic, an offset from the Sun's future position. Imagine the Sun's path as a long arc, and each probe as a faint point displaced tens of light-years from that arc. The final state is two dim markers, separated from home, yet still embedded in the same rotating disk. Even the phrase, "in the sky," becomes slippery, because the sky itself is a projection that depends on where you stand. In 1 million years, nearby stars will have slid to new positions through proper motion, and some will have moved dramatically. A familiar asterism can shear apart, while unrelated stars drift into temporary alignments that look meaningful only by accident. If you tried to point a telescope using today's star charts, you would be aiming at ghosts. This is the reconciliation of mystery with math. A straight line in the Sun frame becomes a corridor in the galactic frame. The corridor exists because tiny angular uncertainties become huge lateral errors after tens of light years. A fraction of a degree today can mean a light year of sideways difference later. The distance estimate stays tight while the sky direction spreads. That spread begins with the limits of measurement, not with any failure of physics. We know the probe's speeds well, but their exact three-dimensional velocity vectors are never measured with infinite precision. Radio tracking gives line-of-sight velocity exquisitely, yet transverse components are inferred through models and long baselines. Over decades, small biases hide inside solar plasma noise, antenna calibration, and ephemeris assumptions. Over 1 million years, those biases become a widening fan. Then the corridor widens again, because the galaxy is not a smooth clockwork. Passing stars add intermittent nudges, and the galactic tide adds slow curvature. Most encounters are distant and dynamically gentle, yet their sequence is not predictable in detail. Deterministic equations still yield probabilistic forecasts when the inputs are incomplete. The result is a plume of possible endpoints, clustered around the best fit drift. The galactic tide sounds poetic, but it is simply differential gravity, an uneven pull across space that bends trajectories over long times. The disk's mass, the halo's dark matter, and the local density field all contribute to that slow curvature. A single stellar passage might barely change speed, yet it can tilt direction by a tiny angle. Over hundreds of thousands of years, a chain of such tilts can matter more than any one event. Chapter by chapter, we built the force budget that makes this honest. Planetary gravity assists set the initial outbound vectors. Then the heliosphere gave way to interstellar space. The termination shock and heliopause were not walls, but boundaries where the solar wind yields to the interstellar medium. Beyond that frontier, the probes fly through a thin plasma, threaded by magnetic fields, where particles are sparse and collisions are rare. Dust and radiation weather the hardware without meaningfully breaking it. The medium is too thin for drag to matter, so inertia remains the dominant term. A grain of dust can pit a surface, and cosmic rays can slowly damage electronics, yet neither effect acts like air resistance. What changes is not speed, but certainty about direction. The probes are like thrown stones in a vacuum, except the vacuum is the galaxy, and the throw lasts longer than civilizations. Cosmology enters here, not as decoration, but as context. The Milky Way is a gravitational ecosystem with streams, tides, and local density changes. Our local bubble is transient, shaped by past supernovae and future encounters. Hot, low-density cavities in the interstellar medium expand, cool, and fragment over time. The night sky we recognize is a temporary arrangement in a moving, stellar volume. 1 million years is enough time for the familiar map to become unrecognizable. Some stars will brighten as they drift closer, and others will fade as they recede. The sun itself will continue its gentle, vertical oscillation through the disk, bobbing above and below the midplane on timescales longer than this chapter, but still not perfectly steady. The probes inherit that motion, then peel away by tens of light years. Their million-year coordinates are therefore a moving target, defined against a moving reference. So the probes do not travel through a fixed star field. They travel through a rearranging neighborhood, where every star has its own proper motion and radial velocity. The interstellar medium is structured as well, with clouds, filaments, and pressure fronts that are invisible to eyes but clear to instruments. In that shifting environment, where becomes a statement about models, frames, and probabilities. The best answer is a range, spoken with humility. Now we return to the object that made this journey matter to humans. The golden record was never guaranteed to be found. It was engineered to exist, to persist as a physical artifact longer than its makers could reasonably imagine. Its gold plating resists chemistry, its etched grooves resist fading, and its protective cover shields it from micrometeoroid abrasion. The instructions attempt to anchor meaning in physics: hydrogen's hyperfine transition, binary notation, and the shared logic of measurement. The record also carries a quiet historical weight. It was assembled in an era when deep space was newly reachable, and when the future felt both promised and fragile. The people who chose its contents knew they were curating a portrait of Earth, not a complete inventory. They selected sounds, images, and greetings that could survive translation, at least in principle, because they were tied to universal constants and simple geometry. Even damaged, the record can remain partly reconstructible if a reader ever appears. Yet, the deeper guarantee is simpler than discovery. The message will exist for a long time, whether or not it is received. Voyager becomes evidence that intelligence once tried to speak beyond its lifespan. It is a time capsule, without an address, carried by momentum rather than intention. The act of sending is the statement, even if the audience never arrives. There is a question hidden inside that act. Who, exactly, is the message for? Is it for extraterrestrial eyes, or for the humans who needed to believe they could outlast themselves? Is it a greeting or a confession that we knew our own impermanence? When you imagine the record turning silently in darkness, you can feel the strange reversal. The artifact is durable, but the makers are brief. This is the closing image we earn by doing the calculation. The probes coast silently, while continents shift and climates swing. Ice sheets advance and retreat, shorelines redraw, and mountain ranges erode grain by grain. Species rise and vanish, and languages lose their last speakers. Human institutions can disappear, and even the memory of the launch can be erased. Still, the trajectories continue, indifferent and precise, because physics does not care who is watching. In that silence, the numbers become almost cinematic. 50 or 60 light years is not a dot on a classroom map, but a gulf of cold, thin space. It is a region where starlight weakens, where the sun is just another bright point, and where the probe's radio whispers have long since fallen below any practical detectability. The spacecraft become objects without signals, pure motion, pure inertia, pure trace. So we resolve the central question in the only form the universe permits. In 1 million years, Voyager 1 is roughly 55 to 60 light years from the Sun. Voyager 2 is roughly 45 to 55 light years from the Sun. In the Milky Way frame, both are near the Sun's future track, offset by those separations after the solar system has moved about 230 light years onward. The best estimate is crisp, while the exact direction is a spreading corridor. The coordinates are therefore double. One coordinate is scientific, a best estimate with a widening uncertainty corridor. The other coordinate is cultural, a marker of what a small world chose to do with its brief window. Even if no one receives the message, the act of sending changes what we are. Voyager 1 and Voyager 2 are the solar system's fingerprints, reaching into interstellar space for 1 million years. We followed two small machines past the last planets, through gravity's slingshots, and across the heliosphere's invisible shore into interstellar night. We watched their power fade into engineering triage, then into silence, while their inertia kept them moving as long-lived test particles. And we learned that the hardest part of wear is not distance, but reference frames. Because the sun itself is a fast-moving ship, sweeping the Voyagers along a changing galactic sea. Their million-year forecast begins with simple arithmetic, then turns into probability as tiny uncertainties widen into a corridor across tens of light years. In the sun's frame, Voyager 1 coasts roughly 55 to 60 light-years away, and Voyager 2 roughly 45 to 55, the exact numbers softened by small forces and imperfect angles. In the Milky Way's frame, those offsets ride on a much larger motion as our solar system travels about 230 light-years along its orbit, turning straight lines into a slow helix through the disk. Along the way, the interstellar medium does not stop them, but it does edit them, grain by grain, with pitting dust, radiation scars, charging and tumbling that can outlast any circuit. And over 1,000,000 years, the real wild card is gravity's weather, passing stars and the galactic tide, usually gentle, occasionally decisive, always capable of nudging the corridor wider than our certainty wants to allow. A close stellar encounter within 1,000,000 years is possible, but not promised, and capture is extraordinarily unlikely without a rare, energy-shedding geometry. The most realistic outcome is quieter and stranger, a continuing drift through reshuffled constellations, while proper motions erase the familiar sky and make toward Ophiuchus or toward Sagittarius only temporary names. Even the Golden Record lives in that same uncertainty, protected by design yet vulnerable in the long run to cumulative abrasion and contrast loss, its message likely to survive longer as an object than as an easily readable greeting. Yet the deepest revelation is not about hardware or even trajectories, but about meaning. When the last carrier wave disappears into the link budget, the mission does not end. It simply stops talking to us. What remains is a pair of artifacts whose paths encode, in their very geometry, the motion of our system through the galaxy, coordinates that are also a kind of memory. So, where will Voyager 1 and Voyager 2 be in 1,000,000 years, when Earth is unrecognizable and their makers are long gone? From the sun, they will be tens of light years out, still inside the Milky Way's thin disk, while the sun has carried their starting point hundreds of light years onward. And from the galaxy's perspective, their location is best spoken as a corridor, an earned humility, a map with uncertainty baked into the ink. The opening question sounded like a request for a pin on a chart, but the journey has turned it into something more honest. Voyager's 1,000,000-year position is not a single dot. It is a relationship between motions, a moving origin, and the quiet fact that the universe keeps changing the coordinate system. If someone, someday, finds one of these silent ambassadors, they will not be meeting our technology at its peak. They will be meeting our decision to send anything at all. Because the most enduring thing Voyager carries may not be the record, or the diagrams, or the gold-plated hope of being understood. It is the proof that a small world once looked into the dark between stars and refused to believe the story ended in silence. In 1,000,000 years, the Voyagers will still be traveling, and the question will remain behind them, like a wake. What else might we choose to launch? Not to conquer distance, but to outlast forgetfulness. If this story moved you, look up once tonight and remember that where is always changing. Then decide what message you want our moving world to leave behind. So, where will Voyager 1 and Voyager 2 be in 1,000,000 years, when Earth is unrecognizable and their makers are long gone? From the Sun, they will be tens of light years out, still inside the Milky Way's thin disk, while the Sun has carried their starting point hundreds of light years onward. Because the most enduring thing Voyager carries may not be the record, or the diagrams, or the gold-plated hope of being understood. It is the proof that a small world once looked into the dark between stars and refused to believe the story ended in silence. If this story moved you, look up once tonight and remember that where is always changing. Then decide what message you want our moving world to leave behind.